of the nuclear engineering students. So without further ado, I would like to invite Dr. Kaiser to deliver his keynote. So over to you, Dr. Kaiser.
Thank you, Mr. Chairman, Dr. Arif Salali, and very kind words and very kind and generous words indeed. I feel small actually, not as gigantic as what you pictured me to be. I'm just happen to be a bystander in all of this. Okay. Before I start, I'd like to welcome everyone. I can see from the list of participants, the chairman of the conference, Professor Narul Hay, the chair of the place where I am at the School of Chemical Engineering and Energy Engineering, Professor Ghazali, is present. And then let me share my file first before I start. I hope you can see this, Dr. Arif. Can you see this?
Yes, we can see this.
Okay then. First, I would like to thank the organizer for inviting me to tell my side of the story of our nuclear engineering academic program. Whether it is a success story or not, it is for you to judge. And I am just doing what, together with my colleague, do what we should to the best of our ability. I hope there is an element of success in all of this. Whether it is a complete success, that is for us to judge later on. Okay, the title given to me was UTM Nuclear Engineering Program. It is very fitting actually because this is going to be my last iNUSTEC before I retire. So this is sort of a swan song for me to take you to our journey, on our journey in running the program from the first inception until now. Okay, and my name is Kaiser Hamzah from the School of Chemical and Energy Engineering, Faculty of Engineering, UTM. I will talk about the rest of it after this. Okay, before that, I would like to introduce our university, my university, UTM. It is located. It is located. Our main campus is located in Johor Bahru, and then our city campus is located in Kuala Lumpur, and then there is our third and new campus in Pago. It is not in the picture there. I was sure that I did everything last night. It is a long way from the center of activity, but still being close to Singapore, we are as busy as Kuala Lumpur is. Okay, and these are okay. Oh, sorry, I dropped my laptop. Okay, sorry. This is our main campus in Johor Bahru, our beautiful campus. I think one of the most beautiful campuses in the country. It is located in a huge area, 1,148 hectares. And then there are many activities that we are holding here apart from education. You'll be welcome to when you are here in this region, just drop by in our campus to enjoy the beautiful scenery there. Okay, this is the school that we are at, right? SKT or School of chemical and energy engineering. This is the old building N01. This is the current building N01A. The signage was not changed. This is an old picture. And then about our nuclear engineering program. Okay. Okay. The need to create a nuclear engineering program at institutions of higher learning in Malaysia was based on the intention. Sorry, I'm doing a few things at the same time. Based on the intention to use nuclear energy as a source of national electricity generation, particularly in Peninsular Malaysia in the post-2020 period. This intention was contained in several cabinet meetings, including the National Nuclear Policy approved in 2010 and Country's Economic Transformation Program, ETP, which is one of the pillars of our new economic model with the objective of making Malaysia a high-income nation. The focus area for implementing this policy was contained in Trust 8, which concerned human capital development. 5 strategies were identified to realize the objective of Trust 8. They were developing national science and technology education programs, developing a continuous nuclear education program, developing national nuclear efficiency and certification scheme, maintain trained human capital in nuclear sector, develop a nuclear education institution. Most, if not all of these strategies were in place already. It is for us to sort of to harmonize it, to improve it, to make it realized. Under the Economic Transformation Plan, we plan to have 2 nuclear power plants to start operating and generating electricity in 2021 and 2022. The dates for these 2 NPPs were postponed to 2030 after the accident at Fukushima Daiichi, and now has been postponed indefinitely. Even though so, we must continue doing what we started to do because it is, to me personally, it is nuclear energy is an inevitable thing. You know, one of these days we have got to resort to nuclear energy to be part of our energy mix. Right. One of the activities that we push forward was education, and then the government decided to have a nuclear engineering academic program run in the country, and then they chose UTM to do that, to run this nuclear energy and nuclear engineering academic program, and we took in the first batch of students in 2012. And the curriculum for the program, the program was devised or formulated with reference to the guidelines issued by IAEA. We also took into account in finalizing our curriculum, took into account the views and inputs of various stakeholders, and we benchmarked our curriculum against top universities running similar programs around the world. Initially, the curriculum was skewed towards the anticipation of having our nuclear power plant. But since then, recently, we sort of tweaked the curriculum a bit to include nuclear technology and nuclear applications courses. but nuclear energy courses still remain. The curriculum must fulfill the requirements of program standards that are engineering and engineering technology by the Malaysian Qualification Agency, the Engineering Accreditation Council, and the Ministry of Higher Education. And then so far we have been audited 3 times by the EAC, and we received they bestowed a total of 10 years of accreditation. The most recent one, a maximum of 6 years of accreditation until 2024. Okay. The challenges we face in running the program, in managing the program. Let me take you through time to when it all began for me. On one fine day, I was summoned by the then dean of Faculty of Science, where I was at, and asked me or instructed me or told me to move to a new program, to a new faculty. When I asked why, he said, we are having a new program that run, a new department that run a new academic program, nuclear engineering program. Then I asked, why me? He said, it is an instruction from the top. So reluctantly, I had to accept. The reluctance was due to I had been at Faculty of Science for more than 10 years. Right? I was comfortable with my own things. I was doing different things other than nuclear engineering because I graduated in 1985. Right. Since then, I had changed my interest towards corrosion and NDT. So when asked to run nuclear engineering program, I was reluctant. First, because it was a new program. Second, I was doing something else. Third, it is also going to be at a new place. Right. But since it was the directive from the top, I had to accept. And then they had one department ready, the Department of Renewable Energy, that would run the nuclear engineering program. Right. And the department was a department of one. I was the only person there. So the challenges were first to get lecturers, right? To run an academic program, we need lecturers, right? And then to get students, and then to have the program accredited, and then to acquire space for laboratories, to buy equipment and instrumentation and instruments to equip our soon to have laboratories. Okay, to get lecturers, we had to travel abroad, even abroad, and of course locally to get those lecturers. And we found it almost next to impossible to get lecturers because the main criteria for the lecturer was and still is that person must be having a nuclear engineering degree as the first degree, at the bachelor degree. But there were not many around in those days. There were a few, but again, most of them were comfortable with their own place, and they were about to retire anyway. Right? So it was difficult to get those in in Malaysia. So we had to travel abroad. Well, abroad meaning here across the water to Indonesia. In Indonesia, traditionally, many Indonesian professors came to Malaysia to our universities to help in our universities in educating our students in those days. Lately, nowadays, there is no motivation for them to cross over because the remuneration package that they are receiving in Indonesia are similar to what they'll be getting in Malaysia. So it was not attractive. I think I made the trip there 3 times. I went to Batam, I went to Gajah Mada University, I went to University of Indonesia. And then unsuccessfully. To say that those were wasted trips was not quite true because we managed to establish a network there. And then eventually, after we exhausted every avenue to get lecturers. Eventually, we managed to gather a number of people, right? And then I was asked, why don't you go to Korea and Japan and other established countries? They have got many nuclear engineers. They were right, but then again, our salary structure or scheme was not comparable to their salary structure, and we cannot afford to pay them king's ransom. They have got to follow what we are having, right? And then the second one is to get students. We limit the first intake. We limit for the first few years. The enrollment was limited to annual intake limited to 30 students only, right? And for the first few years, we quite successfully did that. We received, I don't know how, but there are people, young people, young in the country that found nuclear engineering interested. Hence, we managed to get other students without any problem. And then the third challenge was to have the problem accredited. It was mandatory for any academic program in the country to be accredited by for engineering program by the EAC, Engineering Accreditation Council of the Board of Engineers of Malaysia. And then the fourth one is to acquire space for laboratories. I had to beg around to get spaces, right? Because to have new spaces was out of the question. It would be costing a lot of money, and we did not have the money, so I had to beg. When I went around the campus to look for empty spaces, so to speak, and then I managed to get the required spaces. These spaces were needed for setting up our laboratories, right? And then I can still remember, casually I asked the director of labs, then Professor Professor Mustafa Yusuf, asking him for spaces. He said, okay, just like that, okay. And then when he stepped down, Professor Zamri, the new director, added a few more spaces for us. So we are grateful to the director of labs. And then the final challenge was to buy equipment and instruments. Right. Since our program was there was nowhere for us to ask, to look for example on what to do. We had to go to the internet. Mr. Google helped a lot, and then eventually managed to get the funding and the required instruments. Even though there are a lot more instrument and equipment that we need to make our program world class. Yeah. Okay. After all the activities in facing the challenges, these are our lecturers. Right. Currently, we have got 12 lecturers with various disciplines. Right. And then most of them are from within. Okay. For example, the last in the list, the last three were from our first batch of intake. The best top, the cream of the batch. We invited them to be part of our faculty members. And then we approached Dr. Jasman from Faculty of Science and Dr. Mohsin from Mechanical School of Mechanical, Prof. Narul Hay from UIA. I can still remember when casually as well, I asked Professor Narul, Dr. Narul, come over to JB and join us. Okay. That was song to my ears. No need for me to cajole or to convince. He said, okay. And now he is still here, and he is the chairman of iNUSTEC2021. And Dr. Fadel, we get from guest engineering, Dr. Pechon as well, Dr. Wanahati, Dr. Afifah was my former student when I was at Science, Dr. Harun from gas engineering as well. So we are expecting a few more joining us because some of the current, a few of the current members of the faculty are approaching our retirement point. And then student enrollment, if you look at the table, I cannot explain until now what happened to the 2015 and 2016. Suddenly, the number of intake for that particular session dropped. And it picked up again in 2016. And then in 2019-20 dropped again. That is understandable because of the announcement by the government to not to go nuclear. Right? And then so that affected the number of intake. Currently, we have got 82, and the total enrollment student enrollment is 82. The current and the next session, we do not have the numbers yet. And then so far they have been 1, 2, 3, 5 batches have graduated. 6 batches have graduated, and most of them managed to secure employment in various industry, not only in nuclear industry. The last figure that I got yesterday was the student association conducted a survey on where the graduated students were employed. the response was not good. Only 47% responded, and then the percentage of employment was more than 70%. I think 73%, which is not bad if we consider the current situations that we are in now. And then laboratories. Okay. These are the laboratories that we are having, or we have already have nuclear physics laboratories, which when I took one professor, experimental professor from Hanyang University of South Korea, came to visit our nuclear physics lab. I was surprised when he said, "Your lab is better than ours." Because in Korea, in Hanyang University, they do not have nuclear physics lab for bachelor degree program. They got the lab only for postgraduate program. So that was 1-0 for us, right? And then gamma spectroscopy, we have computer simulation, radar monitoring, nuclear electronics. Well, nuclear electronics, we purposely set up our own nuclear electronics because prior to this, our students were taught by different schools, School of Electrical Engineering. And then they, sorry to say, they do not have a clue what nuclear electronics all about. So they were taught only basic electronics there, so which was not good. Hence, we set up our own nuclear electronics lab. That was the brainchild of Professor Narul. And we also have thermohydraulic labs. I think the first in the country, if I'm not mistaken. We our compatriot in Hanyang University was generous enough to give us their design of thermohydraulic setup, and we constructed our setup based on that. And in non-destructive testing lab, which actually this has nothing to do with nuclear engineering, but then again, one of the techniques, one of the methods used in non-destructive testing involves radiation, so that make it relevant to our program. And then furthermore, the reason we are having a non-destructive lab because we are also running 2 NDT courses with the hope that these courses, radiographic testing and ultrasound testing, would help to improve their employability after they graduated. And then sample preparation and neutron lab, we have a very small, we have the electronics to detect neutron. We have some small neutron sample with strength, and then we would like to improve on that because the main difference between nuclear engineering, nuclear science, and physics is the neutron. We need to be more active in neutron activities. And then the exposure room, currently the exposure room is located at the physics department, faculty of science, which is very inconvenient to get from there to our place. Right? So we are thinking of having our own radiation exposure room to be located around our laboratories compound. So, and then these are the sample of the photos of our lab. This building is T03, is where our labs are located. And this is the thermohydraulic setup. This is the center top is the computer simulation lab. And then the top left is our own mini library. It is interesting to talk about this. You know, in one of the meetings with the Koreans, Professor Stephen Kim of Hanyang University asked me, Haider, what would you like us to help you? That was a blank check for me. I need books. So he sent over books, you know, together with KNA, Korea National Korean Nuclear Station, sent books worth more than 50,000 ringgit. Right. And then these books cannot, some of the books can be obtained, can't be found anywhere in Malaysia. You know? This is one of the book costs right $800 per book. And then so anybody who would like to refer to any of these books, please come over. This is for everyone to read, to use as reference. Okay. And this is our dark room. The top two on the left. Top right is our electronics lab. The bottom ones are for radon lab. Ultrasonic lab, samples nuclear physics lab, top right. And our gamma to hyperpure germanium gamma spectrometer, and then magnetic particle testing lab, and all of these are NT lab. We have got almost everything, but not quite everything. We have got. We want to have more. Sorry, I'm looking at the watch. Okay, got 10 minutes to go. Okay, recently we set up our own research group. Advanced, we call it energy. It stands for Advanced Nuclear Energy Research Group. The areas of interest are as listed: nuclear system design and engineering, nuclear safety and risk assessment, testing, verification, nuclear research building design, nuclear interpretation, nuclear thermal hydraulics, set selection and evaluation, modeling and simulation of new and advanced reactor system. All of these, each area belongs to someone, one of us. So we have yet to embark on the activity of this because we are waiting for grants. Please give us grants. I mean, we need grants, right? And then we have got the knowledge, we have got the expertise. What we don't have is the grant to make it happen, right? And then the future plan is to offer postgraduate academic programs. Well, we should have this postgraduate academic program if we were to be active in our research. We need a new exposure room for radiographic testing. I'm looking for that. We need additional lecturers. We need to set up new laboratories to increase collaboration activities with foreign organizations, foreign universities. Currently, we are doing that with Batan, University of Gajah Mada, and also Chulalongkorn University of Bangkok. And finally, we would like to set up Jabatan JPK, Accredited Training Center. We want to have a center so that we can train our students in preparation for them after graduation. Right? It is to increase the chances of their employability. The JPK, the training center is for NDT only, right? We want to start with radiographic testing first. And then before I end, I'd like to acknowledge a few organizations and individuals for their help on our journey up to now. Organizations such as Ministry of Higher Education, Ministry of Science, UTM, Nuclear Malaysia, LPTA, MNS, IEA, JEA, KNA, Hanyang University, KAIS, the Chinese, CNNC, CZEC, and Tsinghua University, UKM, Uniten, MMPC, Batan, SCTN, ZL Technology, Sdn Bhd, Microspectrum, Sdn Bhd, and numerous individuals who have helped us on our journey to get to where we are now. I must mention these individuals, a few of the individuals, like Dr. Normally Muslim, Dr. Aziz Muhammad, President of MNS, right? Dr. Farid Idris, Dr. Rawi of Nuclear Malaysia, Dr. Yamashita of JEA, Prof. Siwan Kim of Hanyang, our former deans, Prof. Samsuri, Prof. Rahmat, Prof. Zanuddin, and Prof. Ghazali, and many more others, too many to mention. And then without their help, we will not get to where we are now. And I hope they continue with their help until the end, so that we will become a world-class nuclear engineering academic program that can make Malaysia, UTM, and all of us proud. I think with that, I think I would like to end my talk. Thank you for bearing with me. Thank you for listening. Then gracias, merci. Apa lagi? Thank you. I hand it over back to you, Dr. Arif. Or if there is any question, I am willing to. I will try my best to answer that. Thank you.
Okay, thank you, Dr. Kaiser, for the very interesting keynote. So maybe you can stop sharing your slide so you can see who is in the participant right now. You want to see, and also we open like 5 minutes if anyone have any questions for Dr. Kaiser.
Dr. Kaiser, nice to meet you. I think you promote strongly still. Thank you. Very interesting presentation from Japan. Thank you.
Long time no see, Dr. Yamashita.
Yeah.
Glad to see you are still active.
Yeah, I hear very often about you. I hear about you. Thank you. Yeah, thank you. Thank you.
I hope good things. You heard good things about me, I hope.
Yeah, the only good side. Okay.
Tansi Touch, how are you doing nowadays? Tansi Touch was my super senior at London University. So. Small world now. No questions?
Dr. Haider.
Yeah.
Maybe you notice another person here, Tan Sri Tajuddin, is with us this morning.
Yes, I just mentioned him just now.
Oh, yeah.
No,
okay.
it's for Tan Sri Tajuddin tadi Tansi Touch.
Masih my old ears failing me again. Yeah, thank you.
Yeah. Both of you look young, you know. Younger than your age. Good to see and to hear
Morning,
that you are
Prof. Yamashita.
Yes. Yeah. Hello again.
Yeah. Naruru here.
Naruru-san. Yeah.
Yes.
We met on Wednesday, Monday, Tuesday, Wednesday, Thursday.
Yeah,
Yes.
last Thursday. Yeah.
Yes. Yeah. Yeah, good. That the university in Malaysia, UTM, continue to nuclear engineering. I suppose it is a very difficult time for you, but through the nuclear engineering, it is not only nuclear power. There is also application about radiation application. But also Professor Kaiser Dan in United Kingdom. There are many ways to use the nuclear science and technology for socio-economy. Yeah. Yeah. Every time is not a good time. It's a very difficult time for Malaysian nuclear industry. I understand that. Okay, thank you very much.
There's more reason for JEA and Dr. Yamashita to help us. We need all the help from anywhere, especially from the Japanese, from the Koreans, the Chinese, from everyone actually. Our hands are, our arms are open. We would embrace any help from you. Because like I said, it is difficult for us now. The situation is, which is beyond our control. It is just like walking in the sea, you know. One step forward, two step back. But then we have got to strive on, because it is, like I said, it is nuclear energy is an inevitable thing. We do not want to be left too far left behind in this nuclear thing.
Professor, can I say something?
Yes, please, Tantri, please. We are just waiting for you to say something.
Thank you for the invitation to join. I was aware about the conference, but when I was given a link to join, so I decided to join, and it brings back a lot of memories. And your presentation just now gave me a lot of information about something that I didn't realize was going on in UTM because I've left the nuclear field for quite some time. So you remember, I did nuclear engineering at Queen Mary College way back in the mid-70s. And then with Prof. Narol, we went to Oregon State to do a nuclear reactor operations, and we got the license from US NRC to operate the Trigger nuclear research reactor. Came back, worked on the plant and get it commissioned. But then later on, I left, and I left literally for good. Not been involved with nuclear as much directly, but it's always been there until very recently. I've been asked by the Academy of Science Malaysia to chair a special task force to write up policy on nuclear science and technology, but we cannot ignore the need for being prepared for the possible eventual adoption of nuclear power in the system. So this is where UTM and agencies like UTM come into play, because one of the most important ingredients for the future is preparation of the necessary manpower for this sector. Of course, currently it is more about what Professor Yamashita was referring to just now. It is about the application of nuclear techniques in the various other economic sectors, agriculture, medicine, industry, and so on. So again, we need people qualified in that area. So the manpower development is crucial to this area. So I look forward to come and visit you at UTM one of these days. I've been talking to Prof. Narol As you know, I and him, we went back to 50 years ago that we were together in Oregon State. Of course, people like Dr. Aziz, current president of MNS, are all people from the past, as far as I'm concerned. But we are still around. Thank you for this opportunity. I'll be listening in.
Thank you for being around, Tan Sri Tajuddin. Thank you. I can still remember, when I went to your office to ask your view of our nuclear engineering program, and you said make sure that in your curriculum there room for nuclear application. I can still remember that, and it is realized now. It is happening now. We need to not only concentrate on power energy sector, but to the application as well.
But Prof, in that area we have no choice because people cannot wait for that possibility of the eventual utilization of nuclear power. People need to get a job, and job at the moment available not in the nuclear power sector because there is none. So it is in the other areas of application and nuclear technology, in agriculture, in medicine, and we need people who are good in radiation protection, on nuclear safety, and so on. In the other sectors too. So preparing the manpower for all these sectors is where the employment is available right now. But these people can be diverted towards that possible if the country decides to adopt nuclear power as a source of power for the future. And there are things happening in that sector today that may lead to that decision in the not too distant future.
Excuse me. So, thank you, Tan Sri Tajuddin and Dr. Kaiser. So, we would like to proceed to the opening session. So, before that, I would like to thank Dr. Kaiser for the very interesting keynote before, and also the sharing that you had. So, thank you very much, Dr. Kaiser. So, I would like to, we would like to start the opening ceremony. So, with that, I would like to pass the stage to Devi, our MC for today.
Testing 1, 2, 3. Can you hear me?
Yes, we can.
All right. Thank you, Mr. Arif. Wishing you a radiating start of the day with explosive lineups of guests on the Honorary Tan Sri IR Ahmad Tajuddin Ali, the Chairman of UEM Group Berhad, Honorary Prof. Dato Technologist Dr. Ahmad Fauzi Ismail, the Vice Chancellor of UTM, Honorary Prof. Madya Dr. Abdul Aziz Mohamad, the President of Malaysian Nuclear Society, and Honorary Prof. Dr. Muhammad Ghazali bin Muhammad Nawawi, the Chairman of SCEE, distinguished speakers, participants, delegates, ladies and gentlemen. It is my utter pleasure to be here as your Master of Ceremony on this blissful morning. I am Devi Durgashini Anaperempuan Ramesh, expressing my deepest gratitude on behalf of the organizing committee for the pleasurable involvement of all delegates, speakers, and our viewers on Facebook's and YouTube Lives in this International Nuclear Science, Technology, and Engineering Conference 2021. We appreciate your commitments, regardless of your busy schedules, to join us in this jaw-dropping event filled with experts from all across the globe with over hundreds of live participations. For a patriotic beginning, I invite all the guests to prepare yourself for our national anthem, Negaraku. Thank you, dear participants, for involving yourselves to sing along. Before delving further, what better way to kickstart the event than a spiritual boost? I invite Mr. Adam to the floor for Dua recitation.
Thank you, Ravi. Assalamualaikum. Can everyone hear me?
Yes, we can.
All right. Thank you. Before we start, let's start our doa recitation with Kitab Al-Fatihah. Bismillahirrahmanirrahim. Alhamdulillah Rabbil Alamin. Wassalatu wassalamu ala ashrafil anbiya wal mursalin wa ala alihi wa sahbihi ajma'in. Allahumma antas salam wa minkas salam wa ilayka ya'udus salam. Fayyina Rabbana bisalam. Warihilna jannata dar wassalam. Tabarakta Rabbana wa ta'ala. Ya Zal Jalal wal Ikram. In the name of Allah, the Beneficent, the Merciful, praise to be Allah, Lord of the worlds. Let your blessing and your peace be on your servant and your messenger Muhammad and on his family and companions. Allahumma ya Allah, on this glorious day, in conjunction with the opening ceremony of iNUSTEC2021, we uphold our hands to pray gratefully, to thank on your infinite favor to us till we can live in peace and harmony, to perform our tasks as your servants. O Allah, we ask your blessings to make this occasion a success. Allahumma ya hayyu ya qayyum ya zal jalali wal ikram. You are the mercy of the mercies and you are the Lord of the universe. Give us mercy from your presence and shape for us right conduct in our plight. We ask for knowledge which is beneficial and sustenance, which is good, and deeds which are acceptable. ربنا آتنا في الدنيا حسنة وفي الآخرة حسنة وقنا عذاب النار وصلى الله على سيدنا محمد وعلى آله وصحبه وسلم والحمد لله رب العالمين. Amen. Back to you, Devi.
Thank you, Mr. Adam. It is undeniable the growth of a country depends highly on the rise of science and technology. For centuries, our lives are made easier with this constant growth in innovations and new creations. When it comes to the topic of innovations, nuclear technology can be seen as one of the greatest in history, yet with its endless benefits to mankind. Taking that into account, this conference is for you. To get a closer look on what nuclear is all about, to change the negative perceptions of just bombs and weapons, to widen your vision towards a phenomenal outcome. Ladies and gentlemen, iNUSTEC is an annual conference organized by MNS through diverse collaboration with top universities in Malaysia, which is hosted by UTM and NES this year. NES is a nuclear engineering student society which was formed for students to enhance their leadership qualities as well as to boost nuclear awareness among the public. Over the years, they have shown great impact in promoting nuclear technology as students and have made their history to be one of the best student societies in UTM. With all honor, let these 3 days be another accelerating nuclear advocacy journey for all of us. Proceeding with the mastermind behind MNS, the president of MNS, Honorary Prof. Madya Dr. Abdul Aziz Mohammed. I welcome you to the floor. Hello, doctor, we can't hear you.
Testing.
We can hear you,
Yeah.
doctor.
Can you hear me?
Yes.
Okay, thank you, Ms. Devi, for from our Master Ceremony for this conference. Alhamdulillah, saya panjatkan syukur kepada Allah SWT dan sahabat-sahabat tadi yang bisa memandangkan ada kita ada juga saya akan buat ucapan dalam bahasa Inggeris. Okay, so first of all, I'd like to thank to for hosting this conference. And so the thanks goes to Professor Dr. Abdul Ismail, Vice Chancellor to Malaysia, and for to the Professor Dr. Ali.
Excuse me, Dr. Aziz. Mic tak on ya? Mungkin ter-off kot. Boleh dengar sikit je.
Testing.
Yes, we can hear you, but the volume is low.
Testing. Testing.
Yes, we can hear you, Dr. Aziz, but the volume is very low.
Testing.
Yes, we can hear you.
Okay, can you hear me?
Yes, we can hear you.
Okay, so I just how do you speak? So first of all, thank to the Ministry of Malaysia for hosting this our the MNS and the conference. So thanks goes to Professor Dr. Abdul Ismail, Vice Chancellor of the Technology Institute, and to Professor Dr. Ghazali bin Mahmud, Chairman of the School of Chemical Energy Engineering, and then to the Professor Dr. Nahru bin Khair bin Al-Rashid, School of Chemical Energy Engineering, he's the chairman of this conference. And then thanks goes to the Professor Dr. Khair bin Hamza, School of Chemical Engineering, that is the first keynote for today. And also, I'd like to thank to the keynotes from the overseas, Professor Dr. Robert Robinson, from Asia Oceania Newton Circle Association, he is the ex-ANSTO scientist, and to Dr. Fiona Abu Lamasika, Just International Conference Center, and Dr. Imran bin Yusuf, Unity Researchers at College, is a staff of University of Malaysia. Professor Dr. Lee Dr. Associate Professor from School Mechanical Nuclear Engineering, National Institute of Science and Technology, South Korea. Professor Dr. Kim Hee Leong, Associate Professor Department of Nuclear Engineering, National Institute of Science and Technology, South Korea. And Mr. Din Yan, Vice President of China Nuclear National Company. And Mr. Huang Yiling, Deputy Director, Marketing Department, China National Nuclear Company. Professor Dr. Zafar Qureshi, Dean of Graduate School, IISc Pakistan. And finally, Dr. Andres Cruz, Department Manager, Product Management from Antofa, Australia. So today is a very special conference because we managed to organize three events, three conference events, and the conference itself and the post-conference event. And in fact, for the Malaysian University, the conference is very special because MNS today, this year, we celebrate our 33 years anniversary. Then for the keynote speaker, we have very special keynote, Professor Dr. Robinson. He's the AMSA Prize Award 2021. And for the commission, the MNS has 2,000 members. And then last year we formed a new chapter. We called it the Malaysian Nuclear Professional Chapter. So I think this is quite in line with what we done this morning. MNS like to form a nuclear professional in answering the demand of the nuclear professional, nuclear application, and hopefully nuclear energy. So I just finished my speech. We have a good conference for all of us. And then finish with the Wabillahi Taufiq. Assalamualaikum. Thank you.
Thank you, Doctor, for your wonderful opening remarks. Moving on, I invite Prof. Dr. Muhammad Ghazali bin Muhammad Nawawi, the Chairman of School of Energy Engineering, to the floor to give his opening remarks. Welcome, Doctor.
Thank you. Bismillahirrahmanirrahim. Can you hear me, Devi?
Yeah.
Assalamualaikum warahmatullahi taala wabarakatuh. Salam sejahtera dan selamat pagi. Of course, yang berusaha mengurusi majlis, yang berbahagia Profesor Datuk Teknologis Datuk Ahmad Fauzi bin Ismail, Naib Chancellor Universiti Teknologi Malaysia UTM, yang berusaha Profesor Engineer Dr. Nahrul Khair bin Alang Mat Rashid selaku pengerusi iNUSTEC2021 Universiti Teknologi Malaysia, yang berusaha Profesor Madya Dr. Abdul Aziz Mohamed, Presiden Malaysia Nuclear Society MNS, tuan-tuan, puan-puan dan semua yang hadir pada pagi ini secara atas talian. Sidang hadirin yang saya hormati sekalian, terlebih dahulu alhamdulillah bersyukur kita kehadrat Ilahi kerana dengan limpah kurnianya juga dapat kita berkumpul pada pagi Ahad ini dalam satu majlis perasmian sempena dengan International Nuclear Science, Technology dan Engineering Conference 2021 yang lebih kenali sebagai iNUSTEC 2021 secara atas talian. Ladies and gentlemen, please allow me to speak in English for the rest of my speech, especially for the benefits of our keynotes and invited speakers, participants and guests from overseas. But not to worry, my speech is very short. I think it may be less than 2 or 3 minutes. Ladies and gentlemen, we, School of Chemical and Energy Engineering, are very honored to organize the virtual conferencing of the International Nuclear Science, Technology and Engineering Conference 2021 with Malaysian Nuclear Society MNS despite the COVID-19 pandemics. But as they said, when the going get tough, the tough get going, and we survive, the fit survive. Ladies and gentlemen, with this virtual conferencing, of course, we will be missing the customary mingling around during coffee breaks that contributes to faster understandings of human relationships and rapport. But then I believe we have to adjust to the new reality while waiting for the things to return to normal again. And we would renew existing linkages and foster new ones just the same time. I was listening to the conversation between Prof. Haidir and Tan Sri just now. And to be honest, ladies and gentlemen, nuclear engineering is very close to me because we've been through the struggle, especially for the process of getting the accreditation. And we managed, and now we are very proud of the programs. And listening to you, I think cherish the memories from the start of the program, the nuclear engineering program. Ladies and gentlemen, the theme for this year conference, Nuclear Science and Technology for Socio-Economic Developments, fit the role played by the technology and every facet of human endeavors. From the use of nuclear power plants for electricity generation and water desalination, for example, to human health, food security, industrial and manufacturing processes, and environmental preservation. These applications contribute to the achievement of most of the UN, United Nations Sustainable Development Goals, SDG. Ladies and gentlemen, the conference is very special this year because it is a 5-in-1 event, I was mentioned, because it is also a pre-conference webinar which was organized yesterday, a post-conference workshop to be held after the conference, and 2 concurrent events, the nuclear youth competition and the intervarsity nuclear debate. The idea, of course, is to bring together events that would propagate knowledge and understanding across different generations. Ladies and gentlemen, as I promised earlier, my speech is very short, and so we come to the end. So I would like to take this special moment to thank all the participants for this event, especially to the keynote speakers from overseas. I was mentioned from 7 countries, of course, including our own. Your participants are indeed greatly appreciated and would contribute to the enhancements of peaceful uses of nuclear technology. Of course, my sincere and very special thank you to our Vice Chancellor, Dato' Ahmad Fauzi, of course, for his support and for being here with us today during his very busy schedule on Sunday. Thank you, Dato'. So finally, I wish you all, the participants, the keynote and the invited speakers, to have a very useful and enjoyable conference. Thank you very much. Assalamualaikum warahmatullahi ta'ala wabarakatuh.
Thank you, Prof. Ghazali, for the short and wonderful speech. We are finally here for the most anticipated moment of this morning, inviting all viewers to witness the opening remarks by the Vice Chancellor of UTM, Professor Dato' Technologist Dr. Ahmad Fauzi Ismail, and officially launch our conference, iNUSTEC2021. Inviting you to the floor, Doctor. Excuse me, Doctor, we can't hear you. Sorry. Sorry, Doctor, we still can't hear you. Sorry, Doctor, we still can't hear you.
Datuk mungkin boleh tukar mic.
Sorry, Datuk, we still can't hear you.
Technology. Very, very sensitive thing.
Okay, mungkin Datuk ada technical issue, so mungkin kita tunggu dia mungkin restart ke apa.
So I would like to take this moment to actually thank everyone for joining us this morning. A little bit, maybe I can just brief a little bit about what we have been doing in Nuclear Engineering Society and as a nuclear engineering student under this program. So over the years, we have actually organized few events and we have already done few movements as students, thanks to our lecturers, especially Prof. Naro, Dr. Kaize, who have been very supportive in all of our movements.
Can you hear me now?
Oh yes, welcome back, Datuk.
I have to leave. I have to leave first.
The floor is yours.
Okay, sorry for that. Thank you, Devi, for and all the participants for still with us. Bismillahirrahmanirrahim. Alhamdulillahi Rabbil Alamin. Wassalatu wassalamu ala asrafil anbiya wal mursalin wa ala alihi wa sahbihi ajma'in. And a greeting to all. Thanks once again to Devi yang berusaha, Profesor Dr. Mat Ghazali bin Muhammad Nawawi di pengurusi Chair School of Kejuruteraan Kimia dan Kejuruteraan Tenaga yang berusaha, Profesor Dr. Nahrul Khair bin Alang Mat Rashid, pengurusi iNUSTEC2021 yang berusaha, Profesor Madia Dr. Abdul Aziz Muhammad selaku Presiden Malaysia Nuclear Society, dan juga kepada orang yang amat saya hormati iaitu Tan Sri Datuk Dr. Ahmad Tajuddin Ali. Beliau ni nak sebut, kalau nak sebut dia punya tu memang tak cukup lah masa. Tapi beliau merupakan Chairman of SIRIM, Joint Chairman of MITES, Chairman of UTEM, dan macam-macam chairman lagi lah. Dan beliau juga telah diminta oleh pihak ASM untuk menjadi pengurusi task force di ASM untuk nuclear technology. Alhamdulillah, bersyukur kita kepada Allah SWT kerana dengan limpah kurnianya dapat kita bersama-sama pada pagi ini dalam majlis perasmian iNUSTEC 2021 secara atas talian. Ladies and gentlemen, allow me to speak in English, because I would like to address our invited speakers, participants and guests. UTM is honored to host this very international conference, iNUSTEC 2021. I was informed that iNUSTEC is an annual event of the Malaysia Nuclear Society, MNS, and this one is the 10th in the series. Number 10 is very important. So this conference serves as a platform for scientists, researchers, and interested parties around the world to share experiences, exchange their knowledge and new finding on nuclear science, technology, and engineering. The support from international nuclear communities from various countries such as Indonesia, Thailand, South Korea, Japan, China, India, United States, and International Atomic Energy Agency, IAEA, has steered the iNUSTEC 2021 to the international level. This effort potentially to create more research opportunity and collaboration between researchers, scholars, practitioners from different universities, research institutes, and agencies. Nuclear technology has been and is continually being used in many areas of human endeavors such as human health, agriculture, industry, manufacturing, environment, and energy generation. Ladies and gentlemen, even though Malaysia has not introduced nuclear in her energy mix, other uses of nuclear technology calls upon us to explore continue to enhance our capacity and capability in its other peaceful uses. To mention a few examples, the use of radiation in nuclear medicine as a health care approach is well known. In industry, it is used for process quality control, troubleshooting, used for an industrial plant performance improvement. In manufacturing, it is used to produce products and components for specialized application. In agriculture, it's used to produce new plant varieties with better characteristics for phytosanitary treatment. It is also used in sterilization of products such as medical rubber glove by efficient removal of microorganisms. So the application of nuclear technology indeed permeate many areas that related to socio-economic development. So I would like to urge everyone to also promote and inform the public that nuclear technology or nuclear engineering is not the one and the only one nuclear that everyone expect or everyone perceive. I think you understand what I'm trying to say. Nuclear technology can contribute a lot more to mankind. It's not that one, that destructive one. We don't want to promote that. And in Malaysia, I don't think so. We are going to do that. So my deepest appreciation go to the keynote speaker, the technical co-sponsors, and everyone who is involved directly or indirectly for their contribution to make sure that this event is a successful one. I do hope that the conference will run smoothly and all successful. Take care and stay safe. In the name of Allah, the most forgiving and the most merciful, I hereby officially launch the International Nuclear Science, Technology and Engineering Conference 2021 in the name of God for mankind. Thank you. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. Thank you, David.
the ending of that amazing video, it is official. It's the launching of our exceptional iNUSTEC2021. I would like to applaud all your commitments to join this virtual ceremony and history-making beginning of a bright future. Stay tuned with us for these upcoming days of jaw-dropping innovations. We apologize for any technical issues caused along the way. Before ending this launch ceremony, I would like to invite all speakers, participants, delegates, and attendees to turn on your camera for a short photography session.
Okay, maybe we wait for another participant to turn on their camera.
with this. It has a small core, only, a bit bigger than my hands here, but about the size of a garbage bin, at your house. All right, so not very big, and it's a high density core, so it's a higher density material than uranium dioxide, and it's more strongly enriched than in a power reactor, but what we call low enriched uranium, so that's up to 20% U-235. Right, so this is a limit. If you stay below that limit, it's difficult to then take this material and turn it into a bomb. So there are restrictions. It's easier to have uranium below 20% than above 20%. So that's the difference between power reactors and beam reactors. And here's a picture of our reactor while it was building. So this was back in 2003. And the reactor is going to sit on here, and here's some of the piping. You still have to cool this thing, even though it doesn't run very hot. You've got to cool it quite well. And then there's a storage pond goes here, and then you can see out here this land was all cleared for where the experiments are going to go in a big sort of warehouse-like structure called a guide hall. This here is the concrete pump that was used to pour all the reinforced concrete for the reactor. And then here we are a bit later. This is August 2003, and by now they've got up to the pool level here. So, but the roof is still not there, and they haven't actually poured this floor. But this is where the reactor floor level. So the pool goes in here, and the storage pond for spent fuel and other things goes here. And then out the back, you can see where this guide hall is going in. They put the crane, they put the steel structure in on one side, and the crane rail on one side, and these are some lab buildings on the one side. So this is fairly typical. And then you go a little bit later to March 2004. Now the roof is on that guide hall. All right, that's all finished. They built the main reactor building up a bit higher, but they haven't put the crane in yet. And I don't think they'd even put the guts of the reflector vessel for the reactor in there at that point. And they certainly haven't put the roof on. All right, so that's just a brief introduction to reactors and beam reactors, research reactors. The other method you can use is spallation. Here you take a beam of high energy protons and you fire them into a heavy metal target, which could be clad tungsten or liquid mercury. That's what people use mostly these days, but they have also used tantalum, lead bismuth, eutectic, and even depleted uranium. Now, spallation is actually more heat efficient, as I pointed out at the beginning, per neutron. For each neutron you get you get much less heat. So if you want to make steam, this isn't good. But if you want a bright neutron source and you don't want to have to get rid of the heat, this is good. All right. So it's more heat efficient than fission by around 20 times. All right, so if you want to make a very bright source and the main problem is getting rid of the heat, spallation is 20 times better. Now, it's not quite as simple as that because you have to cool your target, this heavy metal target, and maybe with water or heavy water, and you also have to put some container in there that's not a good neutron material, some stainless steel or Inconel or something to contain it all. So in an engineered system, it's about a factor of 10, not 20. All right, but it's still more heat efficient than fission. So what this tells you, this factor of 10 tells you that when people talk about a megawatt spallation source, that's roughly equivalent to a 10 megawatt reactor in terms of time average flux. But most spallation sources are pulsed in time. Typically, a short pulse every 20 to 60 times per second. All right, and they are driven by pulsed accelerators. So it could be a rapid cycling synchrotron, which is what the New China spallation neutron source has, what ISIS in England has, what J-Park in Japan has, or it could be a LINAC plus a storage ring, which is what the American facilities like SNS and Lance have. All right, these are all circular machines. All right, and so what you do is you pile up your protons in the circular machine, and then you spit the whole lot out in one go onto the target, and the pulse length that you get is characteristic of the circumference of of the ring. So, you know, that's going to be, you know, of order 100 meters. And what that tells you, just to move this, so what that tells you is the proton pulse length is typically around a microsecond. If you just take the speed of light and divide that into, you know, the distance, that's what you get. And it's not quite as simple as that for the neutrons, because the neutrons then have to moderate. So that 1 microsecond gets spread out by the moderation time. Now, if you don't have the ring, a linear accelerator on its own gives you about a millisecond in pulse length, or maybe more. And this is what's going into the European spallation source in Sweden. And it's even more complicated in that the accelerators don't have to be pulsed. If you have a big cyclotron, that will give you a continuous beam. For instance, like, it's still a spallation source, but it's continuous, like the SynQ source in Switzerland. But for us as users of beams, it's pretty much, you use it like a reactor. It's the characteristics are very similar to the reactor. All right, and spallation looks like this. Here, you know, it's an old slide, but you take 800 MeV proton, fire it into tungsten. You get, you know, excited states, evaporate off some neutrons. See, a lot more than 3 here. And the higher the energy, the more you get out. And then you actually get some secondary reactions, and they release neutrons as well. All right, so that's why you get so many more than the 3 with fission for each proton that you put in. And the target, you know, it might look like this. This is the target of the J-Park spallation source in Japan. So this, I think, is an Inconel container, and inside it's got liquid flowing mercury pumped through it. There's all the pumps and stuff is in this trolley here. So this is sort of the equivalent to the fuel in a reactor. And then the proton beam comes into this window along the front here. But nuclear physics goes on with megavolts, as you know, mega electron volts. And we want to study materials, we want milli-electron volts, not mega electron volts. So we've got to change the neutron energy by 1 billion times, by a factor of 10 to the 9, right? And we do that with moderators. So fission produces an energy of about 2 MeV per neutron. Fusion would produce 14 MeV. Spallation can go to very, very high energies, up to the proton energy, up to a GeV, you know, which actually can cause you shielding problems. Excuse me a minute. So people talk about fluxes and power levels for reactors and spallation sources. Typically for a reactor, people talk about something called the unperturbed thermal flux. This is what you would get out of the reactor if you had no holes in it. So you had no beams and no cavities in it for, you know, a cold source or something like that. And, you know, for a typical 20 megawatt reactor, you will get 4 times 10 to the 14 neutrons per square centimeter per second. The best beam reactor in the world in Grenoble produces 4 times that. Okay? But in the beams, we get a lot less, right? So the neutrons, like, you know, they're very hard to steer or focus or anything like that. So they come out in all directions. And the beam only takes a small range of angles. So typically, the flux in the most you can get in a beam is about 10,000 times smaller than this. So the best beams are about 10 to the 10 neutrons per square centimeter once you're outside the reactor. Pulse sources, you know, they're actually, because the pulse is on for a short time, you actually then think about the peak flux. So for the IBR-2 reactor in Russia, its peak flux is up at 10 to the 16 during the pulse, and then it's off. And that's equivalent to, you know, almost 2,000 megawatts in the pulse. And of course, you can't cool that continuously, which is why they pulse it. Spallation sources, they tend not to quote it this way. They quote the power in the proton beam. And that's simply the product of the current and the energy of the protons before they hit the target. So 100 microamps of protons at 1 GeV will give you 100 kilowatts average power. And a megawatt would be a milliamp at 1 GeV. All right. So when they talk about that, that's what they mean. Now, to moderate, we've got, these are the sort of some of the materials you might use. whether it's a power reactor or a research reactor, you might use graphite or water, like in a pressurized water reactor, or heavy water or beryllium. Now, water's great. It scatters brilliant, and this number's big, all right? So that's why it's very good as a moderator. But if you look at how much it also absorbs a reasonable amount, all right? And what really matters is the ratio of the two, all right? So that's what you get. The ratio of those two cross sections of water is 250. If you go to graphite, it's much better, all right? And heavy water, better still. And beryllium's not too bad. And in fact, this is to the point that you can build a reactor just with natural uranium and run it with graphite or heavy water, and you can go critical and you can have a reactor like that. Whereas with heavy water, you can't. You have to enrich. You have to get some more uranium-235 in to even make it go. All right, but the best material we've got as a moderator is heavy water, right? And so most really good beam reactors, high flux sources, are heavy water reactors. And if you want cold neutrons, liquid deuterium is the best moderator for the same reason. It's just the ratio of these, the scattering and absorption cross sections. But because it scatters less, that means the neutrons have to go further before they collide again, and they can lose some energy. All right, so everything becomes bigger. So like a CANDU power reactor is going to be much bigger than a pressurized water reactor. And a liquid deuterium cold source is going to be bigger than a hydrogen cold source. And the other thing, of course, is then the moderation times are longer. So if you want very short pulses, hydrogen is going to be better than deuterium if you have a pulse source. So to try and change the spectrum, people put sources into a reactor. So most beam reactors these days will be built certainly with a cold source and maybe with a hot source. So if you put a block of graphite in your reactor, it will, close to the core, it will naturally heat up to around 2000 degrees C, and then your neutrons will come out with this temperature rather than, room temperature. And the reactors in Grenoble and Munich have such a hot source. Cold sources are more common. The opposite occurs. If you have a bottle of liquid hydrogen at, say, 20 Kelvin, then you go the other way and you lower the energy of the neutrons come out. So people use hydrogen, and there's a question whether it's boiling or supercritical, and you can make it pure parahydrogen, which is good, or in the case of deuterium. So deuterium is better, and that's what's used in Grenoble, PSI, in Munich, and at ANSTO. And people have used methane, it's both liquid and solid methane, but they have some problems. So the spectrum that you get out of a moderator is, if it's really just the neutrons are a perfect gas in thermal equilibrium. So if you have a very big moderator, perfect gas in thermal equilibrium, this is the spectrum that you'll get. And this is basically the temperature, KT, right? And I'll show you some curves of that in a minute. So the spectrum you get depends. It's called the Maxwell-Boltzmann distribution, all right, in classical thermodynamics. On the other hand, if you're not in thermal equilibrium, so if you put in very high energy neutrons, like for our megavolt neutrons from nuclear reactions, and there's not going to be much upscattering. Everything's going to be cooling down or slowing down. You get a 1/E spectrum like this, and so this is sometimes called a 1/E or slowing down spectrum. All right, and you get this at spallation sources. You get it at reactors as well, because you're putting in high energy neutrons. So the sort of curves that you get look like this. So the Maxwellian gives you this bump here, all right? Bump here. And so this is room temperature. If you go to the graphite, 2000 degrees, you move the curve to the right. If you go to cool it down, but with liquid hydrogen, you go to the left. So if the science you want to do is down here in the millivolt range, a few millivolts, all right, which might be tens of angstroms in wavelength, you're going to be, 30 times better with a cold source in your reactor. And you look at that, okay? And so that's for reactors, and it's similar for spallation sources. The moderation's the same, but you get a longer tail going to higher energies. And you can clearly see this 1/E. So this is a log-log scale. You can see this 1/E spectrum here. It's there in the reactor spectrum as well, actually, but not quite so obvious. So this is a section through the vessel, if you like, of our reactor in Sydney. And this is the concrete shield out here. So all this metal stuff, concrete. Then there's a swimming pool reactor. So this is water. Then there's a vessel with heavy water in it. And in the middle is the core with the fuel. All right, the fuel's here. It's just 4x4, 16 fuel elements. And then the neutron flux spreads out in this reflector vessel. And we look, this is our source right here for thermal neutrons. And then for cold neutrons, this is where our bottle of liquid deuterium sits, right here. And then the beams go out through these tubes and then into what are called neutron guides, through shutters, and then out to the experiments. Okay? And the cold neutron source looks like this. This is an aluminium alloy container, multi-skinned, and it's filled with, because you've basically got this thing sitting at 20 Kelvin, about a meter away from something producing 20 megawatts. So it's got to be well insulated. So this is filled with liquid deuterium. Ours actually has a cavity in it. And that's what the neutron beams look at for the cold source. And the spectrum, you know, is there where I said about 10 to the 10, all right? Neutrons per square centimeter second. And then, so here's a picture of the reactor, if you like, the shell of the reactor. So this is all heavy concrete. And I'll have to move picture here a bit. You can see where some of the beams come out here on one side, and then on the other side there's a bunker, all right, that goes out to the experiments. This is inside the bunker, and the guides come out like here. So these are the stainless steel vacuum jackets for the guides. So this is like an optical fiber carrying the neutrons out. Inside it looks like this. So here's the vacuum jacket, then you've got some glass, a glass box with float glass, very smooth glass on the inside, and then fancy metal coatings on the inside of that, and inside vacuum. So it's a flight tube with vacuum, and it's actually curved along the length, so you can't see straight down it, but with reflections you can. So this we use to carry the neutrons away, and these are typically about 5 centimeters across, up to 30 centimeters high. And here's a shutter, all right? So we replaced the shutter in 2012, and they've just done another one earlier this year, and it's complicated because it's got 4 guides. You see here all the glass, 4 guides all together going, and then this is the rotating shutter, and this is the piece that goes upstream of it. All right, so that's what that looks like. And then going out into the guide hall, you get something like this. So these are this is the picture from Munich in their reactor. So the guides are coming out of the reactor, and then the instruments or the experiments are on the end like this, and then some of them are not so obvious, all right? A few of them come out on the side like this here. And this is what our reactor looked like before we put any instruments in. So you can see the end, we're looking towards the reactor. This is the end of the bunker for thermal neutrons, and there's the end of the bunker for cold neutrons, and the cranes are there for where the instruments are going to go in. They're all there now, but they weren't when this picture was taken. And that's more or less what it looks like now. This photograph's a little bit old, but you can see 2 big small angle scattering machines here in the corner. There are 4 diffractometers over here. There's a reflectometer there, some other instruments up there. They're not very obvious. All the equipment for changing temperature and pressure and so on, magnets and so on for the experiments are here, and then some labs over on the side. So all I've talked about so far is just the spectrum of neutrons you get out of the reactor. But to do a real experiment, we want to know the energy of the neutrons or the wavelength, all right? And there's basically two ways that you can determine that. The first is you can diffract from a crystal or reflect from a crystal face like this. So the neutrons come in, they reflect from the crystal. These are the rows of atoms. And, depending on the spacing between the atoms, you get constructive interference or not. All right. And so what this will do is if you put a polychromatic beam in here, it will send out just one wavelength with this wavelength according to this formula. So that's a way of specifying at particular wavelength. And, you know, you can do that with X-rays as well. It's the same physics. Or the other way is by measuring the time. If you've got a pulse of neutrons, you can just measure the time. You know how far they've come from, you know, wherever the source was. And using the de Broglie relation, you get this formula where the wavelength ends up proportional to the time over the distance. All right, so that's called time of flight. And we use both of those methods. Here's an example. The crystals aren't actually on it, but this is what a crystal monochromator put the graphite crystals on these blades. So a modern one, it's not just one crystal. I mean, here we've got 9 of them, all arrayed on these aluminium sheets here, and all driven with motors and everything. So they focus, but you can see how they're at an angle. They focus horizontally, and then they can also they're on a mechanism here, so they focus vertically as well. So that's what a modern monochromator would look like. So if I first talk about diffractometers, you can do it 2 ways, really. Constant wavelength or angle dispersive, which is very much like an X-ray diffractometer operating on copper K alpha. So then you've got a 1 wavelength and you scan angle, or you can do time of flight where you pulse the beam, and then you go wavelength dispersive. You have a fixed detector, you don't have to move anything, and you just scan the wavelength. Right? Those are basically the 2 methods. So if you have a neutron beam coming in, you monochromate with this crystal, go to your sample, you get diffractive peaks here, you pick them up in all these detectors. They've all got their own collimators, and you have to move this around a little bit to fill, you know, so that you get a continuous pattern. And that's what it looks like. This is the one at NIST in Washington, D.C. It's quite an old machine. So the reactor's over to the right. It comes out here. The monochromator's in the shielding down here somewhere. The beam comes here. Here's the sample, I think in a cryostat or a furnace, I'm not sure which. And then the detector bank is here, right? So that's what we do. And our machine in Australia is very similar. And if you go to the ILL, it'll be similar there, all right? This is our collimator box for our diffractometer here, all right? So very nice, all, you know, and we had 128 detectors behind this. This is before it was installed. On. And if you do it by time of flight, the neutron beam comes in from your pulse neutron source, the sample is here, and then you have an array of detectors here. The best ones are in backscattering, and you just pick up the signal. Nothing moves. And it just measure as a function of time. So you need fancier electronics to do all of this, but we know how to do that now. And this is what, you know, a modern powder diffractometer looks like. This is the one in near Hong Kong, in China. So here's the spallation source target station. You know, the moderators are in here right in the middle. Your neutrons fly out through a vacuum tube. The sample's here. The detectors are it all looks very boring because it's just lots of shielding and you can't see any of the details. But it looks very boring, and but yeah, it works quite well. And if you want more intensity, you know, you can get rid of the collimator and get a very, very good detector. This one has about a square millimeter resolution. And you just sit there and count. It's just like film, electronic film, but you can't get quite as good resolution as you do that. So this is Wombat in Australia, but there's a similar machine, D20 in Grenoble, and you can do similar things. For instance, GEM at the ISIS spallation source can do similar things. I think I'll skip over that. So look, the other main methods are for looking at nanostructures. And the 2 methods are small angle scattering and reflectometry. So, you know, and what we want to look at is things on the scale of 1 to 100 nanometers, 10 to 1,000 angstroms. Now, you know, if you take this formula here, Q equals 2 pi over D, and there's the Bragg relation. If you want D to be much bigger, you know, going up to from an angstrom to 10 or 100, you want D to be bigger. It's in the denominator. We want lambda to be big and theta to be small. So we want small angles and long wavelengths, which is cold neutrons. And we use these methods to study whole proteins, whole polymer molecules, microphase separation, defects in metals, vortices in superconductors, pores in porous materials, skyrmions, which are very fashionable now for magnetic storage and things like that, and coatings, nanoscale coatings and interfaces, right? So the experiments in principle are very similar. In SANS, but we typically have a transmission geometry, whereas in reflectometry, we have a reflection geometry from a smooth surface. In SANS, we use a pinhole, and in reflectometry, we use a line geometry, right? Because the surface is flat, we can use a line. We use slightly coarser resolution for small angle scattering, about 10%, and a big 2D detector. I'll show you some in a minute. And reflectometry, slightly better wavelength resolution and a smaller detector. So here's the SANS machine at the China spallation neutron source near Hong Kong. And again, it doesn't look very complicated, but here's the sources over here. You come here, the sample goes here, and then the detector sits in this vacuum tank here. All right, and it's a very simple experiment. You just need source, collimator, sample, detector, really. It's a very simple, conceptually a very simple experiment. And here are the components of our first one in Australia. This is the thing that gives you the 10% bandwidth. This is the rotor for the velocity selector that gives you, so crystals give you too good resolution. You don't want, so you use this thing called, it's like a turbine, that the Archimedean screw that the neutrons can go through. It's absorbing plate. So this thing spins, and depending on the speed, that gives you the wavelength that you use. So that sits in this blue box here. And then you have apertures in this evacuated box, which isn't fully installed yet. So that's 20 meters of this, and then another 20 meters of vacuum vessel, all right? And the detector sits inside this. So this was actually when it left the factory in Melbourne on the way up to our reactor, came as one piece. And here are our two SANS machines with the back off them open. So there's one type of detector in one and another type of detector in the other, all right? So this one's a 40-meter SANS, 20 plus 20. This is a 35-meter SANS. This one's time of flight with choppers. This one's constant wavelength. So everything I've said so far has assumed no change in the neutron energy at the sample, as in X-ray, as we're assuming. It's often called elastic scattering, but it's really total scattering. Now, normally the elastic scattering is much stronger than the non-elastic or inelastic scattering, so this is reasonable to assume it's elastic, but it's strictly not. But if we measure both the instant energy and the final energy separately, we can actually measure the inelastic scattering as well. So there's another set of spectrometers that we use to do that, and I won't go into all the details, but basically I told you you've got these two methods. You've got to determine EI and F, and you can use crystals or time of flight in any combination. So crystal, time of flight, time of flight, time of flight, time of flight, crystal. So if you just use crystals front and back, this is as in a triple axis spectrometer and typically the reactor. If you use time of flight throughout, that would be like in a chopper spectrometer. And, you know, it's used a lot at spallation sources, but also at some instruments at reactors where you have a set of choppers. You need more than one. And then the other is where you use a crystal and time of flight, and a few very good instruments at reactors. Our own Pelican in Australia and iNUSTEC at the ILL do that. Or you can do the other way. It's called inverted geometry, where you have time of flight and then you analyze with the crystals after the sample. So this is inverted geometry, and that's typically done at a spallation source. So the Tosca instrument at ISIS or DNA at JPark, which is a backscattering spectrometer. Here's a triple axis spectrometer schematically, all right? So you come out of the reactor, there's a crystal here, you go to the sample here, another crystal set at a different setting and out to the detector. So you measure EI with this angular setting and EF with this angular scattering. And the components look like this, right? This is sort of, they all move around on air pads on a polished floor. So this was in the factory for where they made all these stages, but that's what they look like. So look, just to look at the fleet of instruments we have in Australia, we have 4 diffractometers here, 2 SANS machines, plus an ultra SANS machine in here, 1 reflectometer, and there's another one gone in here now actually, so there are 2. a couple of spectrometers, cold neutron spectrometers here. They're quite big, expensive things. 2 triple axis spectrometers, one built by Taiwan. And I haven't talked about this at all. This is neutron imaging. So just the neutron equivalent of CT scanning like you have in a hospital. All right. So, but we typically do it on, we don't do it on human beings or even animals, we do. But we might look at fossils or engineering components. And in Japan, at the J-Park spallation source, which is the best we have in our region, they have, 23 beamlines here, all doing similar but different things. All right, so that's what they've got. And now, just to summarize, here's a table, which I hope you find useful, of some of the leading reactor sources. All right, so in Grenoble, Munich, Washington, us in Sydney, Korea, China, Oak Ridge, all right? And they've all got cold sources and they've all got guide halls like I showed you with various different powers, but you can do a lot with 20 megawatts like we have, or like NIST is up here, we're down here, Opal, yeah. And then there's the pulse reactor from Dubna, all right? The one pulse reactor, but most reactors are steady state. And the leading spallation sources, well, today the leading ones are in Japan at J-Park and at Oak Ridge in the United States, which Oak Ridge is now 1.4 megawatts and will go to 2 megawatts soon. So they're probably the best. This one's very good too, not as powerful, but they've been doing it a long time. And the newest is in Dongguan near Hong Kong in China. This is just starting up quite well. The long pulse spallation source being built in Lund in Sweden. All right, which is slightly different. And then the continuous spallation source that I mentioned, Syncue in Switzerland. And I think that's the end of my talk to fit in the half an hour you gave me. So I'll finish there, and I'm very happy to take any questions. Oh, was I too fast?
Thank you, Prof. Robson. So I think I may allow one question from the audience. Is it okay, Prof. Robson, to have one question?
Okay, no, thank you very much. I am Yamashita from Japan.
Oh, hello.
I was former director for research department of JAEA.
Yes.
Yeah. After accident of Fukushima Daiichi, yeah, the JRR3 was stopped for 10 years. Now JRR3 has started, yeah, in operation. Please put the JRR3 in your slide in the table.
I should. Yes, I knew it started. Congratulations. At the time that so I first wrote this talk about 4 years ago, and of course. You were there, but you were not operating. Yes, of course. I'm sorry.
Yeah, thank you very much. It is very so proud that the JR3 recently started. Thank you very much.
Yeah, no, you're welcome.
Very interesting presentation.
Okay, thank you very much, Dr. Yamashita, for the question.
Yeah,
I should say briefly, we were very happy to welcome people from Japan to Australia. So we offered straight away in 2011 after the earthquake, and they kept coming for a long time actually, while JRR3 was down, and there was a wonderful collaboration between Australia and Japan. So I think we all benefited from that. But we're glad. I mean, not many places are running right now because of COVID right at the moment. So maybe JRR3 is, and I'm just doing reviews for Oak Ridge, and they are running. The reactor's running in Australia, but they're not allowed to do science at the moment. But that should change in the next few weeks. But if you look at it at the moment, I think not many places are running well just because of the restrictions on people moving around because of COVID.
Yeah, thank you very much then.
So that's my last question for you, Prof. Robinson. Recently, I got email regarding the news that the Australian government will spend some money on the new facility for radioisotope. So what is your comment?
Oh, yes. So look, so our reactor's a multi-purpose reactor. I mean, it really has two or three purposes. So we produce molybdenum-99, and its daughter is technetium-99M, which is used for medical imaging. And we've been doing that for a long, long time in a facility that was built in the 1950s and has all sorts of problems, reliability and safety problems. And so there's been a push for quite some time now to replace it with a modern facility. All right? I mean, there's two parts to this. First, you have to separate the molybdenum-99 out from the uranium material that you use. So that's a sort of wet chemistry process. It's a bit messy, actually. And so we've already got a new plant to do that. And then you take that molybdenum-99 and you have to put it into a little machine that can go to the hospital called a generator. And you might want to prepare other medical isotopes as well. And that's done in a different, so the first part is sort of like a bulk chemical process. And the second one is actually preparing everything so it can go to a hospital or a radiopharmacy. And it was time to get a new, if you like, factory to do the latter. And that's the money that's just been approved. Well, it's not, there's money for design, all right? They haven't actually got the money to, haven't got the money, as I understand it, haven't got the money to build it yet, and they're looking for private sector involvement, so we watch this space. But it's basically good news. Look, the other big piece of good news I heard in the last week is that the South African government is giving money for them to build a new research reactor just outside Pretoria, both for radioisotopes and for beams. And I imagine they're going to do something very similar to what we have done in Australia.
Okay, thank you, Prof. So I think if I have a chance to get the visas, so we will see you in Buenos Aires, Argentina.
I hope so.
Okay, and have a good luck for your new facilities in Opal. Okay, thank you. So
well,
thank you very much.
Thank you very much.
Okay, so I hope everybody will enjoy the Prof. Robinson presentation, and I hope for the young students, young researchers, please keep in touch with Prof. Robinson for the using the other regional facilities. Thank you again. Bye.
You're welcome.
Thank you.
Okay, so the next speaker we will Dr. Yamashita from Jaif. Okay. I think I know him when he's engaged with mission to the UTM. Okay, so so now I let Dr. Yamashita to deliver his presentation. Okay, so the word is yours, Dr. Yamashita. Please.
Yeah. Can you hear me? And also, can you see my
yes.
my presentation material?
Yes.
Yeah. Is it clear?
Yes.
Okay. So nice to meet you, Aziz-san. Yeah. After a long time. I'm very happy to see you. Yeah. You are still active. Okay. I have studied in Malaysia. Tuan-tuan dan puan-puan. Selamat pagi. Assalamualaikum. Okay. Okay. I'm really so truly glad to be invited to the International National Conference of Malaysia Nuclear Society. Thank you very much for the invitation. Okay. And so I have many friends in your countries, but I would like to introduce myself. I'm the Kiyonobu Yamashita. okay here, of the JIFE International Cooperation Center. I was actually the director for HRD Center of the JAEA. Yeah, I have enjoyed very much with the many friends from Malaysia. Now I'm working the more, so focusing the, how can I say, distributing the Japanese safety technology of the NPP to NPP embarking countries. Yeah. Today, I'd like to present about the nuclear science and the technology for socio-economic development. Aziz-san, can you hear me well? Okay?
Yes, yes, yes.
Yeah?
Yeah, I can
Okay.
hear you very well. Yes, good. Thank you.
Oh, very nice. Thank you very much. Yeah. Okay, then next page. Yeah. Before to start going to my main theme, I'd like to report the present status of Fukushima. I assume you're interested what Japan now is.
Yes, yes.
Yes, yeah. I'm very sorry that the Japan occurred the accident of the Fukushima Daiichi. Yeah, I'm very sorry for that. Yeah. But the Fukushima Daiichi, the commissioning is in progress. You can see visitor can stand the about 100 meter close to the Fukushima Daiichi NPP plant. It was done the accident. Yeah. Yeah, you can see the visitor have no mask. Yeah, no problem. Yeah, now due to the COVID, visitor have the mask, but not due to the dust, radioactive dust from NPP or something. It is very well, how can I say, progressed. Also, you can see a big crane. They are operated remotely from other side, other position. Yeah. And okay, later you can visit please visit the following URL. Yeah. You can see inside of Fukushima Daiichi very clearly how now is it. Yeah. Okay, this view graph shows the Fukushima revitalization. The upper part, it shows the unit 4. After a hydrogen explosion, it was broken as shown in picture. Now it is, how can I say, repaired. It was necessary to repair this facility to remove the spent fuel from this facility. The old fuel was removed from spent fuel pool. It is completed. Also, the infrastructure restoration near Fukushima Daiichi accident, Daiichi, is like that. This highway is about 4 kilometers from Fukushima Daiichi unit, NPS. And they are already restored 2015, and it is already used. Also, the railroad was restored, what can I say, March 2020. Therefore, you can take the train, Joban line, from Tokyo to Sendai, the school here. Yeah, please visit here with your radiation detectors. You see how reduce that. Okay. But also you have a strong concern about the tritium boy alive your countries. Many boy visit your countries. This view graph shows the I read the nuclear facility both at home and abroad in tritium is discharged as liquid waste into the river. For example, in France or something, the NPP are constructed near river and the sea, and also into the atmosphere through the ventilation process in compliance with the domestic law and regulation. Okay. And the Fukushima plant to release the tritium waters less than 22 T is, how can I say pronounce, trillion becquerel. But please see that the CORI in NPP in normal operation release the tritium annually already 91 trillion becquerel. It is about 4 times more. Also, you can see the PWR in China, close to Malaysia, released the already 98 trillion becquerel in normal operation. Yeah, please keep this real situation. Many nuclear facility release tritium to see. Yeah, because the PWR, they use the boron acid to control the reactivity, and they make the nuclear reaction, and it became tritium. Therefore, the PWR release more tritium than BWR, and the release of tritium from Fukushima is much less than of them. Please keep remember that. And the next page, and this tank, it contains the tritium contaminated waters here. And after the release, the environment radiation dose very slightly increased. Its natural radiation in Japan, in average, is 2.1 millisievert. But by ocean release, the 0.00007 millisievert per year may be increased. I think the influence to Malaysia is negligible, and I can say there are no effect to your countries, I think. Okay, now a little happy side of Japan. This view graph shows the NPPs restarted and in operation. We are planning the 39 reactor to restart again. And here 10 reactor was restarted already. Yeah. Also, these reactors are standing in very nice landscape. Also here you can see Mihama number unit 3. It is behind the you see the unit. Yeah, there are many people are enjoying the swimming in summer. Okay, now I would like to start with the mine assignment. I would like to present about nuclear science and technology for socio-economic development. Yeah, nuclear socio-economy consists of the nuclear. Okay, I am too fast. Yeah, I can go slowly. Anyone, if you have a question, you can stop me anytime. Okay. The nuclear society economy consists of nuclear energy and radiation application. I would like to start with radiation application. Yeah, radiation is used in various fields as very useful tools. Yeah, for example, tomography, computed tomography, X-ray photograph, food preservation, material modification, water flow survey, thickness meters. Yeah, for example, the steel industry, they use the very hot steel. This steel will be the thickness will be measured with radiation, gauging, chemical analysis, and chemical composition. But surely we have to always consider the negative effect, negative health effect, such as cancer. Yeah, but we have so many opportunity to do with radiation application. Okay, yeah, I'm very interested in this physics of the positron emission tomographies. Yeah, the fluoride 18 compound, it is a positron emitter, is injected in human body, and it will be accumulated. This composition is accumulated extra in cancer area, because cancer accumulated, they try to accumulate many things in their cell. And the fluoride compound emits the beta ray. The beta ray takes the electron around there, and they produce two photons. They flight in anti-direction. Yeah? From detector, with detector, they determine the position of the where this photon come. Photon come from the cancer area. The position of cancer will be determined from two gamma ray that fly in opposition direction. It is wonderful physics, wonderful application of the radiation. Yeah, if you have idea with radiation, many idea, you can develop many interesting tools. So it means that you can make a business. Also, this view graph shows the boron neutron capture therapy. It was carried out in the JRR4. It is I think the ideal cancer therapy. For example, boron compound is injected to body, as they are selectively collected in cancer cell. As I said, cancer cell accumulate or eat every material. They cannot decide it's good. This food is good or not. The normal cell selects that, but the cancer cell does not select good compound or bad compound. Then cancer cell accumulate the boron compound in cancer cell. After then, neutron beam from reactor irradiated to the area of cancer cell part. And then in cancer cell part, boron make a reaction with the neutron and become alpha particle and lithium. The flight length is about 10 micrometers. It means this high energy alpha kill selectively the new cancer cell. It is ideal. Any good medical doctor cannot take out selectively only cancer cell. But this, the boron neutron capture therapy, it make possible to kill only the cancer cell, and the normal cell are still be alive. It is ideal cancer. This is also nice application of radiation. Also, this is a treatment of the result after boron neutron capture therapy. It's before that. This is medical irradiation for malignant melanoma on the soil of the food. After 3 months later, a little injured, but after 6 months later, cancer was removed. A normal, how can I say, surgeon, the patient food should be killed. So how can I say, take out, cut, about close to the full food, feed. But with boron neutron cancer therapy, it is well healed by this therapy. Okay, and also the radiation application gives the so different many interesting opportunity. The life cycle of the melon fly. Yeah, please start. Yeah, melon fly are very happy and mating together, and after then they give the egg. Egg becomes the larvae, and these larvae feed the fruits and vegetables, and the fruit will cannot be sold, cannot bring to the market. Yeah? For example, if you have nice fruit, and you cannot export this fruit to other countries, and then, okay, this larvae become a pupa in soil and marsh, and born again female male, and they produce again they make mating and egg. But if you put the sterilized male by irradiation, and this sterilized male disturb this mating, and after then, by sterilizing male melon fly cannot produce its offsprings. They cannot, no children or offspring are produced. Then this view graph shows the eradication of melon fly by radiation in Okinawa Island. It's a south island in south of Japan. Yeah, the sterilized fly are put in the environment. At the number of the sterilized fly increase, but the normal fly decrease after several years. Yeah. 3 years, and then there are no more melon fly in Okinawa. Then the vegetable from and the fruits made in Okinawa can be bring to the Japan, the main island, and also export to the other countries. And the farmer get more money from this nice mango. How is it in Malaysia? Do you have also mango? Can you export your mango to every countries? Okay, it is my favorable application, radiation application. My favorable application, radiation application, is a neutron activation analysis. Yeah. Then when material absorb neutron, they become radioactive. Yeah? And the radioactive ray precursor to the material are then emitted in the activation analysis. The element composing the material, including the extremely small amount of the impurity in material, can be determined by measuring such emitted radiation. Yeah. If I visit every go abroad, and I try to get the soil a little, and I bring it to home and to make the neutron activation analysis, then I find the easily if there is gold. Yeah, it is a very nice method. You can very small amount of gold you can detect also. Yeah, this is a very nice method. Yeah. Okay. This view graph shows the conclusion about the radiation application and economics stayed in Japan. The industrial use of the radiation application gives the 2.22 trillion yen. Trillion yen. It's a big amount. Also, the medical use brings the 1.91 trillion yen money. And agriculture, the use the 0.2 trillion yen. Yeah. Total, the radiation application bring 4.37. Yeah, about 4 trillion yen. It's a big amount of money. The main for industrial use, this for radiation is very well used semiconductor processing, and it is very famous. Also, you drive a car, and every time you use the radial tire, the manufacturing of the radial tire is this radiation is inevitable. Also, medical use, PET, CT, cancer screening, and the potato or agriculture potato sprout stop. If you find if you have idea, you can find many nice business or find interesting tool. If you understand the radiation very well, you can find your idea and find the contribute to the socio-economy. Yeah. Okay, I back. As I said, socio-economy, nuclear socio-economy consists of nuclear energy and radiation application. In Japan, the business with the nuclear power plant is about 5 trillion yen. And radiation application already, as I said the last view graph showed this about 4.37. Yeah. So Raf said the trillion yen. Actually, the business with radiation application is comparable with the business with the nuclear power plant, nuclear energy. Therefore, yeah, I remember very often about several years ago, I am invited by the Professor Kaiser to UTM, and I have given the lectures. Besides the NPP, I have given the application of the radiation application. Yeah, and I explained there is also many possibility to do the radiation application. I often remember that. Okay, now I'd like to start a little mention the nuclear energy business. Yeah, how many NPP are necessary to supply the whole electricity power for all population of Malaysia? The population of Malaysia is 33 million. And I estimate for 1 million, you need 1 gigawatt electricity. It means about 1 person, 1 kilowatt. Yeah, 1 person, 1 kilowatt, 1 million per population, 1 gigawatt. It means 33 gigawatt. Maybe it is not so good to cover the energy demand only with NPP. Maybe 1/3, maybe 10 NPP is very well to have NPP. I think in Malaysia, yeah, and NPP are very useful to stabilize power supply. But your country have many concern about the radioactive waste management. In Japan, yeah, there's a different method to contain or keep the radioactive waste management. the space disposal, it is a very not so high reliability. And also ocean dumping, this is banned by London Convention. It is a nice idea, but it is also the ice sheet disposal. It means you bring the radioactive material to the Atlantic, Antarctic area, and the radioactive waste is a little hot, and ice will be melt, and the can with the high level radio waste fall down during the melting the ice and fall down. After then, this water will be frozen again. I think this is a very nice method, but this is also banned by treaty. Therefore, we have only the geological disposal, and with Japan, we decided to do the geological disposal. The high level radioactive material will be disposed 300 meters deep in Earth. And surely you have concern, maybe it makes the, how can I say, the barrier will be intact, and the radioactive material can decay. After rough calculation, it shows maybe after 6,000 years, can alive a small amount of radioactivity, and after 6,000 years about, and very slightly the natural radiation may increase. This is the effect. It was calculated. Okay, it is a decision. Technology is already given, and I think the Malaysia is more stable than Japanese ground, I think. Okay. Okay, next one, Japan, the JAEA promote to develop the high temperature gas cooled reactors. Surely with this reactor, we can produce the electricity. Also, we can use for the gas turbine electricity production with gas turbine. But this reactor is now developed to produce hydrogen. This reactor we are able to have the heat of 950 centigrades, and this makes we can make the hydrogen from these waters directly, and it does not produce any carbon dioxide. Yeah, and this is the fuel. Okay, and also fast breeder reactor is very useful to use the uranium. For example, now we can use only the uranium 35, only 0.7%. If we have the fast breeder reactors, we can use also 99.3%. We can use as fuel for NPP. Then we can have about 16,000 years energy, but actually about 5,000. Okay, I think anyway most important is the education to obtain benefit of socioeconomy from nuclear science and technologies. Okay, I skip that. Yeah, we support Japan Nuclear HRD Network, supports the education in elementary school, also high school, university, and also young researcher, and also foreigners. Japan Nuclear Network support the education. And also we check very much the description and textbook in the middle school, secondary school, high school, and so on, and improve the textbook. And also, yeah, I have been in Malaysia. I have seen visit the secondary school in Kajan. This school give very nice lecture. What is the nuclear radiation? I impressed that the Malaysia do very well. Lecture about radiation and the nuclear in science, technology, engineering, math in the secondary school. It is very nice. Yeah, I hope Malaysia keep this this education. And I personally hope that HRKD network will be continued by the support of the Nuclear Malaysia to promote the nuclear science and technology for the socio-economic development in Malaysia. Actually, this network is, how can I say, established by the effort of the MNPC, but this is no more there. And I hope that the Nuclear Malaysia take this position and keep this network, promote the education, nuclear science technology for socio-economic development. Okay, thank you very much. I say the summary, Fukushima is in vitalization, and there's many interesting radiation applications that contribute for socio-economy. The socio-economy of radiation application is comparable large to that of the nuclear energy in Japan. And LWR, FBR, HTGR contribute for the socio-economy that for the reduction of carbon dioxide. Education about nuclear and radiation is necessary to develop the nuclear science and technology for socio-economic development. I think it is wonderful that Malaysia promotes the science, technology, nuclear, engineering, and mathematics STEM, and include this radiation and nuclear in this STEM. Thank you very much for your kind attention. Thank you very much. I'm finished. Okay. How can I say video stop? No, I can show you.
Okay. Do you have any?
Okay, any question?
Yeah, I open to the audience. Any question to one question or two questions?
Yeah, Prof. Yamashita. Wateshwa Nahru Sandes UTM Karang.
Nahru-san, yeah.
Nahru, yeah. Yeah, I have actually three questions from your presentation. Very interesting presentation, by the way. One is on the Fukushima. So, what is the plan, the future plan for the site? Is that a new reactor will be there, or what? And secondly, is that on the
okay? One question. My brain is not so good.
Okay,
so
okay, all right. Sure,
you asked about the Fukushima.
Yeah, Fukushima. What is the future plan after everything is rehabilitated at the current site of the reactor? Is anyone
your question is what we'll do with the Fukushima Daiichi after
something? Right.
Oh, it is no more possible to rehabilitate the Fukushima Daiichi. We will do only decommissioning. Okay.
Okay. All right. The second one is that on the socio-economic contribution of nuclear science technology that you mentioned about 4.27 billion yen in 2015. What is that in terms of percentage GDP?
GDP?
Yeah.
Yeah, I don't know exactly GDP, but I know only the Japanese Japan's budget. Total budget is about the 100 trillion yen.
Oh, okay.
Yeah, total budget, the governmental budget.
So that'll be around
4%. 120. Yeah, okay.
Yeah. All right. Okay, that's good. So probably we need to check also how much will be impact of the use of nuclear technology here in Malaysia. Yeah. Maybe
Last question?
the last one that I would like to ask from you is that you mentioned that you estimated that 1 million population will require around 1 million 1 gigawatt, right?
Yeah.
Yeah. So I'm looking at Japan, for example, have about 126 million population, and you have around about 40, 50 nuclear power plants. So how do you come up with the remaining power from what sources?
Thank you very much. Then, okay, then we use not only the nuclear, we use also import the natural gas from Malaysia, and we call coal. Therefore, the very roughly said, maybe the 1/3 of the total demand of the new electricity supply should be the nuclear. Then you can stabilize very well. It means about 10. Yeah.
I see. Okay.
And also the 1 gigawatt per 1 million. Yeah. If you see you have the 200 volt. Yeah. And every house you have the breaker. You know breaker.
Yeah.
Electricity breaker. And you multiply with the volt and divided by your member of the house. Every house, every person is very roughly 1 kilowatt are necessary.
Yeah, right.
Yeah, okay. Okay?
Okay, arigato. Yes.
Hey, domo, terima kasih. Yeah. Yeah.
So, last question from the audience. From the student, your ex-student.
Yeah, the Mr. here, the laughing, the Alif was my student about 7 years ago. Yeah, I remember very well.
Yeah, we met in Tokyo.
Tokyo also, and also the in UTM.
Yeah. Okay, I don't have any question, but thank you for attending our conference.
Yeah, thank you much. I was very glad to meet all of you in Malaysia. Yeah, Adil-san also, you also, many, Kaizuru-san.
Okay,
thank you very much.
Dr. Mashita, this is my opinion. So I've seen your slide in the networking, but I don't see how NGO, okay, like our Malaysian Nuclear Society or other nuclear society to play a role in your networking.
Yeah. Your question is why the nuclear society should not work. Yeah, surely you can work. Yeah, network is not only one. You can cooperate very well with the Nuclear Malaysia, maybe. Already you cooperate very well to how can I say, to hold this very nice conference like that. But sometimes for the network, some money are necessary. Yeah?
Yes.
Usually the nuclear society is not so rich. you can invite something or something to do that. Yeah, Nuclear Malaysia get more the how can I say maybe the more contact with the government.
You know, because why I raise this, because in many technical societies, we don't have industry people to join because to them they don't see this important. But I believe that we need the industry to join this society, so they can see what is the social economy that can benefit to them. So that's why if you can NGO can come into the networking, and then these industry people can see the importance of these the technologies to them, because like you said, then by then they can see how much money they can make in 10 or 20 years time on the nuclear application. Okay? So that's my opinion.
Yeah, thank you very much. Yeah, anyway, yeah. I hope this network, which is established by the MNPC, it will be kept for the nuclear science technology for socio-economy. Yeah.
Okay.
Now it's difficult to keep for nuclear power, but the nuclear society, socio-economy is very good. It can be kept. Thank you very much.
Okay, thank you
all of
again,
you.
Dr. Yamashita, for
Yeah.
sharing.
Jumpa lagi.
Bye-bye. Yeah.
Bye-bye.
Yeah, kios ticketed,
Hai hai, domo.
Domo. Okay.
Domo domo.
Domo.
Okay.
Dr. Aziz, your mic is mute.
Okay. So thank you to our two keynotes, Professor Dr. Rob Robinson and then Dr. Yamashita. Okay. So I hope we can meet you again. And I hope if we can travel to Japan, I'd like to meet you in Tokyo. So we have more discussion on how to make MNS rich.
Yeah.
Knowledge.
Yeah.
Okay.
Let's do that.
Yeah.
After COVID, surely we meet again. Yeah.
Yes. Okay, so I give back to the Master Ceremony to continue this conference. Thank you very much.
Thank you.
Bye-bye.
Bye-bye.
Yeah.
Okay, thank you, Dr. Aziz, for sharing the previous two keynotes. So we would like to continue the conference with the first paper presentation session, okay, which is the session number 2. The theme of the session is environment and safety. It will be chaired by Dr. Nur Shazwani binti Muhammad Ali, which is my colleague over here in UTM. Over to you, Dr. Shazwani.
Dr. Shazwani, we cannot hear you.
Okay, I hope that you can hear me. Sorry for that technical error, probably my headphone is not working. So once again, thank you. So we're going to continue our event with second session, which is the first paper presentation from the participants. So for this session, we're going to have 4 presenters from UTHM, and 2 from Nuclear Malaysia, and another one from University Technology Malaysia. So I think just a little housekeeping before we get started. So if let's say you have any question during the presentation, you can just type your question in the chat box, and I will bring them up during the Q&A session. And for the presenter, just to remind you that you're going to have only 20 minutes presentation, and including the Q&A session. So I hope that that's all the housekeeping that I want to mention here. So without further ado, I think I would like to invite our first presenter, which is Dr. Ahmad Hassan Salihuddin bin Muhammad Sarif from University Tun Hussein On, Malaysia, for your presentation. Over to you, Dr. Ahmad Hassan.
Okay, Assalamualaikum warahmatullahi wabarakatuh and good afternoon. Thank you very much to Dr. Shazwani. So let me share my screen first. Can you see my screen?
Yes, sure. I can see your screen.
Oh, okay. So, so my name is Ahmad Hassan. The title of my presentation is Time Independent Reliability Analysis for a critical reactor safety system based on the fault-free approach. These are my contents, typical contents. So I will start with probabilistic safety analysis. So PSA or PSA, so probability safety analysis or PSA is an important safety assessment tool for nuclear installation, especially for nuclear power plant. Okay. And the main objective of PSA are trying to answer the following questions, which are what are the possible accident sequences, chronologies that can occur at the nuclear installation, okay, and when the accident sequence occurs, we want to know how likely, or what is the frequency of the sequence. And finally, due to the accident sequence, what are the possible undesirable end states that can occur. And for the modeling tools in PSA, mainly there are event tree and fault tree, which we use event tree to identify the possible combination of success or failure of our safety system or our mitigation system in response to the initiation of the accident. And we use fault tree to systematically and logically model the reliability of our safety system or our mitigation system. So PSA has been systematically grouped, and the grouping is called PSA scope. This is for the systematic classification of the level of analysis. So if you see the vertical axis, that's the level of PSA. We have level 1, level 2, and level 3, and the horizontal axis is the type of hazards that can cause, that can start the accident. There are many involving internal events, internal flooding, internal floods, and so on. Okay, and the axis pointing towards ourselves is the amount of the reactor operation if the PSA is performed for nuclear reactor. And if we consider the innerst box, which is the level 1 PSA during the full power operation, and the cause of the accident is the internal events. What should I say? The common hazards that usually thought of is the loss of integrity of the primary coolant boundary, meaning that the reactor is losing the coolants. So the coolant is not only to during normal operation, the coolant is not only to transfer the heat, but it is also a protection for the nuclear fuel. Okay, so when there is a loss of coolant, or let's say a break, the amount of coolant will be reduced, and eventually, if the core is uncovered from the coolant, okay, the core will become the source of hazards, okay, because we will experience the rise of fuel temperature, and after that, that situation will damage the nuclear fuel core. Okay, that are one of the reasons for every plant there is or there are a dedicated safety function, okay, to provide emergency cooling function. Okay. So to recover the loss of coolant inventory, and as well as to provide long-term cooling to remove the decay heat. And so the motivation of this study is to to look into the reliability and specifically the how the reliability changed as the time goes by. Okay. Reliability of the emergency cooling system at a nuclear power plant. Okay. So this involves the failure mode and effect analysis for each of the component in the system. Okay. And then after that, the construction of the port 3 and the quantification of the port 3. For in this particular study, the graphical construction of port 3 and the quantifications are performed using a Spectrum PSA computer software. Okay, we have selected an advanced pressurized water reactor, which is the Korean Advanced Power Reactor 14,000 or APR 14,000 for its safety injection system. And the scenario that we analyzed is the post large break loss of coolant accident. So how does the system, the SIS system, perform during this particular accident condition? So this is the schematic diagram of the SIS. There are 4 trains, namely train 1A, train 1B, train 2A, and train 2B. And each train will inject evaporated water from the IRWST or the in-vessel refueling water storage tank during the post large break loca into the reactor vessel via direct vessel injection. Via direct vessel injection nozzle into the reactor vessel. Okay. However, for the success criteria for the long-term cooling after large break loca is that evaporated water must be continuously injected via train 1A and train 2B, because only at train 1A and train 2B, other than through the direct vessel injection nozzle, the evaporated water also injected into the vessel through the hot legs. So from train 1A and train 2B, evaporated water is injected through the direct vessel injection nozzle, and as well as through the 2 hot legs of the reactor. Other than IRWST in the system, there are also safety injection tank. But in this particular case, for this particular analysis, we don't consider the reliability of the safety injection tank. Other than that, there are a series of valve and check valve, and also importantly, the safety injection pump. So the methodology involves FMEA, failure mode and effect analysis. So this is to identify and screen out. Identify the relevant component and to screen out the unrelevant component. And then to consider the effect of the failure of each component to the functionality of the SIS system during the post large break loca. And by doing the fault tree modeling and quantification, to model the fault tree, and to quantify it, we use the outcome from FMEA. And then with the fault tree calculated, we can further evaluate each of the contribution from each of the basic event. And then also from the base fault tree, we also try to look at the effect of operator recovery action to the reliability of the SIS. So these are the result of FMEA. Okay, so all the components listed here components that shown in the previous figure, the previous schematic diagram. Okay, for especially for the pumps, there are two failure modes, FTS, which is fail to start, and FTR, fail to run. And the last column, they are reliability parameter. Okay, so this is the failure probability of fail to start, and that is the failure probability of fail to run. Okay, and okay, sorry about that. And then other than that, the valves, valves can fail by fail to close or fail to open. Okay, and same good for the check valve. Is fail to open, and we also we screen out the basic components such as RWST, SIT, and pipes. Okay, and all the reliability data taken from NORAC document. So this is the constructed for 3. So the top event is the failure, long-term cooling failure by the SIS. Here, immediately below the top event, there are 2 intermediate events. So each corresponds to the train 1A and train 2B. So this intermediate event is connected to these 3. Okay, and okay, after the quantification of the base fault tree, so this is the these are the minimal cut set lists that are obtained, especially for time at 30 minutes after the initiation, and the top event. The failure probability of the system is this value. And unfortunately, single failure, okay, and any single failure of the basic event will lead directly to the failure of the SIS. Okay. And this does not comply with the single failure criterion. And if you can see the top contributor, the safety injection pump failed to start, but in the long run, specifically at 5 hours, the first 2 at the top are replaced with still the pump, but a different failure mode, which is the fail to run. Okay, because the fail to run of the safety injection pumps increasing with time. Okay, whereas other basic event have constant failure probability. Okay, so this is the failure probability of the SIS with time, and specifically at 72 hours, the failure probability increase 6 times. Okay, and again the same reason, because of the safety injection pumps fail to run. Okay. So we can think of other measures, okay, to increase the reliability of the SIS, such as operator recovery action. I will come to the operator recovery action later. So now let's take a look at the fase basic importance. Yeah, so by definition, fase basic importance is the ratio of reduced unreliability or ratio of increased reliability when a basic event is completely reliable. It means that it does not fail at all. Okay, and particularly for the pumps, if we can find a way to make it not fail at all, okay, the benefit is 100% increase in reliability. Okay, and for other basic event, their value are not that significant. They are less than 1 per 1,000. Okay, and so the same reason that I explained just now for this outcome. Okay, if we consider a human intervention of human action, okay, so this one, it is found out that the mean unreliability of the SIS decrease by 2 order of magnitude, okay, from 10 to the minus 2 to 10 to the minus 4, okay, by introducing a nominal human performance, okay, 0.011. This is the value from SPAR-H method. Okay, and we can see, okay, the minimal cassette now. We can see the compliance of single failure criteria. Okay. So there is no more single basic event that lead directly to the failure of SIS, and now we can see the combination of the human calculation and the failure of the hardware. Yeah, so to conclude our works, so we perform the time dependent for the analysis for the SRS, okay, and a failure mode and effect analysis was inevitable, and we use digital data from similar industry from the new REC document, and the degradation of SIS with time is mainly to the safety injection pump, and with the introduction of human calculation, we can see the reliability improvement, and in practice actually there is a human recovery action. But for the analysis, I first commit the human calibration, and after that I include the human calibration to see the effect. And however, we omitted many important basic events such as human errors, electrical power failures, basic components, and the electronic of instrumentation and control. We also didn't work on the common cause failure, and we only consider the mean value of the reliability parameter for all basic events. Okay, we neglect the distribution parameter of the basic events. Yeah, I think that's all from me. Thank you for your attention.
Okay, thank you, Dr. Ahmad Hassan, for your presentation. So I think from the chat box we don't have any question yet. So probably to the audience, if you want to ask, you can just write in the chat box so that we can discuss together with the presenter. But since we're running out of time, so I think we need to proceed to the second presenter. Once again, thank you, Dr. Ahmad Hassan, for your presentation.
Okay.
So
thank you.
All right. Okay. But to the audience, if you want to ask anything, just left it in the chat box. So we can read it after if we have time after this. All right. So for the second presentation, it will be presented by Dr. Maizura Ibrahim from Agency Nuclear Malaysia, if I'm not mistaken. And she will talk about applying empirical method for performance metric measurement of a nuclear security system. So I think I left this floor to you, Dr. Maizura, for your presentation.
Thank you, Ms. Chairman. I hope I'm here loud and clear, but unfortunately I cannot share the screen here. The button is unavailable.
Oh, meaning that in your panel, in the bottom panel, you don't have share button?
Yes.
So I think we can share it for you, I think.
Okay. Thank you.
Please wait for a while. I'm sorry. Please wait for a while. We're still finding for it.
result give us the acceptable result or not. And in rush measurement model, we have techniques to determine whether the result is acceptable or not. And if they are not acceptable, then we have to go back to the third process, which is we have to re-identify the development and for the pilot environment. And then the next phase is to implement the real environment. If we got the acceptable result, and then we implement it, we implement the survey to the real environment, and then we evaluate the result and analysis using RASH measurement model. And then after that, we have after we have the result, we present and report, and the process will be end. Next. All right. This is the methodology comparison based on 3 methodology name, and then the properties that we are evaluated. Okay. The first methodology we evaluate is the system-based evaluation methodology, and then the second methodology is the theoretical and hypothetical based, and then the third methodology is the empirical based, which is our methodology. Okay, in terms of requirement, we have for the system-based methodology, we need to develop a complete system. A complete system needs to be designed, developed, and implemented in the nuclear facility environment before the performance metric could be measured. And then the second, for the theoretical, hypothetical based methodology, of course, you don't need to have a complete system, but you need to design the DBT. Thus, DBT must be developed first, and then for our methodology, we didn't need DBT or a complete system to be developed. We only need the framework that is going to be used as the basis for the application system development. And for the time consume properties, for the system base, we have long process, and for the theoretical base, it is moderate, and for empirical base, we have low time consume, because it is considered low time consume. And as for the risk, high risk for the system base, as it's you have to have a complete system, and then if the system fail, and then you have to go for a long time process again to evaluate the system. And then for theoretical base, we consider it low risk, and then as for our empirical based methodology, we have we consider it low risk. And in terms of process complexity, you can see that system based evaluation is very high, and theoretical based methodology is very high. And then in terms of complexity, the empirical based methodology is very low. Okay, next. Okay, in conclusion, in this paper, we propose a methodology for evaluation of nuclear security systems. The key element of the methodology are developed by applying empirical method, implemented by distributing the online survey questionnaire, and this online survey questionnaire could be re-implemented on any survey platform. And then we apply rush measurement model in analysis and constructing the result, and this is a very precise cycle evaluation. And this methodology has low time consume, low risk, and low process complexity compared to the previous methodologies such as system-based and theoretical or hypothetical-based methodology. Next. Okay, I would like to acknowledge the IEEA and the research grant J0 2011 for providing the grant for this project. Next. And this is the references. That's all for my presentation, and thank you very much.
Okay, thank you, Dr. Maizura, for your presentation. So, from my point of view, I can see that the empirical method is quite efficient. If you want to compare to others method, like the one that you mentioned just now. So,
Okay.
I just want to ask, since we don't have any question in the chat box, is this method is just only on the proposal state? It's not yet being implemented.
Yes,
Or
yes, it is on the proposal state.
so is there any future work on this has been conducted, or it's
Yes,
not
we
yet?
currently in the process of validate this method with the IEA team.
I see. All right. Okay, it's good to see, because big data is actually more or less not same, but it has the same concept like artificial intelligence. Am I right? Or
Yes, yes,
yeah.
yes.
So okay, all right. Thank you so much, Dr. Majra, for your presentation.
You're
So
welcome. Thank you.
for the audience, do you have any question? You can just raise your hand, or you can unmute your mic to ask Dr. Majra regarding her presentation and her project. Okay, I think I assume there is no question for now, but if you have it, don't worry, you can just type in the chat box and we can reread again after this. All right, once again, thank you, Dr. Majura, for your presentation.
You're welcome.
Okay, so we're going to moving on to the next presentation. I can see our presenter is here, Mr. Samesh Raj Partasaranti. And he will be presented on the radio frequency. Oh, it's not same. I think I just give the floor to you, Mr. Samesh, for the presentation.
Okay, a very good afternoon, Dr. Shazwani and also members. Before proceeding further, is my voice clear and is the slide visible to you guys?
Yes, I can hear you clearly, and your slide is also in a full screen.
Okay, all right. So the topic of my presentation, or more of a knowledge sharing, is radio frequency radiation safety assessment from MTBS, which stands for Mobile Telephone Base Station. A case study on variable time averaging duration. Okay, my name is Shamish Raj Parthasarthi, and I'm from the Radiation Safety and Health Division, Malaysian Nuclear Agency. All right, this is my presentation outline. First, on the introduction, I'll just introduce on the overview of that, and then the objectives, the methodology, results, discussion, and finally the conclusion. Okay, the recently published ICNIP, which stands for International Commission on Non-Ionizing Radiation Protection 2020 guidelines, it specified that the reference level at any points are to be averaged over any 30-minute period over the whole body space for frequencies between 100 kilohertz up to 300 gigahertz. So, keeping this in mind, a study was conducted in order to investigate the effect of the time averaging duration from the RF radiation from the stated mobile telephone base station. The measurement was conducted generally in 5 locations where all the mobile telephone base station, or MTBS in short, were installed. The assessment was conducted at 3 variable time averaging, specifically at the 1 minute interval, 6 minutes, and finally the 30 minutes interval. All right, before dwelling further into my research, so let me just give you a brief overview. All right, so mobile telecommunications, particularly mobile phones and the mobile telephone base station, they play an essential part in the model telecommunication. So as of first quarter 2021, there were 44.4 million mobile phone subscription in Malaysia itself. And then it is estimated at the end of 2021, there'll be 31.76 million smartphone users in Malaysia. And currently, there are around 25,000 telecommunication structure in Malaysia itself. So this figures shows that how important the mobile telecommunication structure is important in order for us to get a better connectivity in terms of mobile phone coverage. In addition, my study or my knowledge sharing will focus mainly on the non-ionizing radiation section. So generally, the non-ionizing radiation section is more of a 3 kilohertz up to 300 gigahertz, which covers the TV and radio broadcast, mobile phones, microwave and satellite. But my study specifically covers the mobile communication from 800 up to 3 gigs only, right? So the objective of my study is first to investigate the effect of the time averaging duration on the power density from the radio frequency radiation from the MTBS. Secondly is to compare the power density value against a different time averaging duration, specifically the 1 minute, 6 minute, and the 30-minute interval time. And then finally, to determine the level of radiation present and to assess the potential exposure received by the general public at the vicinity of the structure. Right, so if you can see in my slide, this shows the 5 main locations where me, myself, and my team conducted a safety assessment. They are first mobile base station, second, third, fourth, and finally the fifth mobile station. And generally, the method of our assessment was we performed a spectrum or the scan around the mobile telecommunication structure. Example, you can see the green oval. We covered the whole location or coverage of this, and then we conducted the safety assessment around this area, and we have analyzed data on the highest radiation level. So to put the things into perspective, this figure shows the point of measurement. Generally, the measurement indicated was selected based on the worst case situation where it's a accessible location is facing the antenna beam. So as you know, the place where the radiation will be high when you are facing air exactly at the antenna beam, and also at popular public places such as residential areas, bus stops, and also the playgrounds, right? So the methodology of my assessment would be first is to identify the RF source. So technically for this RF source will be the antenna itself. Next is the identification on the point of measurement. As I mentioned in my previous slide, it was based on worst case situation, right? Third is the measurement procedures. We followed the procedures recommended by the ITU, International Telecommunication Union, IEC, International Electrotechnical Commission, ICNIP, International Commission on Non-Ionizing Radiation Protection, and also the IEEE, Institute of Electric and Electronics Engineers. Each point of measurement, the measurement averaging was taken for 1 minute, 6 minutes, and 30 minutes using the NARDA broadband meter with a probe of EF0691, which has the capability to measure the frequency range from 100 kilohertz up to 6 gigahertz, right? And the measurement was performed at 1.5 meters from the ground based on the standard by the IEC. And also the results were recorded in power density, specifically in microwatts per cm square. And finally, the results was compared with the reference level or the permissible exposure stipulated in the MCMC and the ICNIP standard. So to get a picture, this is how our typical safety assessment was conducted. If you can see in this picture, the antenna, and then we have used two particular equipment. First is the broadband equipment. Okay, this covers the whole spectrum from 100 kilohertz up to 6 gigs. And then next is we use the selective radiometer, which covers the specified frequency based on the frequency from the service providers and also based on the code. Right. Again, this picture also it shows the things how we do the measurement. Example, when you have a radiation emitted from the antennas, and then the technical personnel is recording the data. All right. So you can see the transmit power generally from base stations is less than 100 watts, and then the length or the height of the equipment was placed at 1.5 meters from the ground, and the results were recorded in terms of power density for each duration: 1 minute, 6 minutes, and 30 minutes. Right. So this is the reference level. So if you can see, this was taken from the ICNIP and the MCMC mandatory standard. So for our case, it's of the frequency of 2 gigahertz up to 300 gigahertz. So the reference level was stated at 1000 microwatts per cm square. So keep this in mind that this is the main reference point of our safety assessment study. All right. So based on this, we have conducted the results. So you can see from the first mobile telephone base station, you can see that it's arranged according to the time averaging duration, the highest measured power density, the reference level, the comparison with the reference level, and also the percentage of changes compared to the 30 minutes. So please bear in mind that the reference level was at 30 minutes because 30 minutes will be our benchmark point or the reference point. If you can take example, at the time averaging duration of 1 minute, all right, so the highest measured power density was at 1.70 microwatts per cm square. And then if you can see at 30 minutes, the power density level was at 1.84. So how we get the reference level, all right, how we compare with the reference level? First is in order to get the reference, to compare with the reference level, we take the highest, you can take the example of MTBS1 for first minute duration and see at 1.70 microwatts per cm square, you divide it by the reference level, as I stated just now in the ICNIP standard and also the MCMC standard at 1000 microwatts per cm square, and then you times with the percentage, you'll get the 0.17 percentage, meaning that the results obtained is only at 0.17% of the permissible exposure limit or to the reference level. And next is how we compare the percentage of changes if we compare to the 30 minutes. So as I mentioned just now, the reference point will be at the 30 minute. So if we can take to get the percentage of changes, so you can take the power density of 30 minutes, you need to minus with the power density measured at 1 minute or 6 minutes, and then you divide it by the power density at the power density measured either 1 minute or 6 minutes, and you need to times with the 100%. So example, if you can take for the percentage of change for 1 minute compared to the 30 minutes is at 8.2 percentage, and if you want to compare the percentage of change, the increment from the value, if you measure at 6 minutes to 30 minutes, is at 1.1%, right? So the same principle and the same calculation, it applies to all the mobile base stations. For mobile base station 2, 3, 4, and 5. So I will, to put the things into perspective, so these are the results. So if you can see, this is the graph of the percentage of change against the location of the mobile base station. All right. So if you can see from the graph, you can see that at the mobile base station number 1, if you compare the percentage of change with the value of 30 minutes to the value of 1 minute, the percentage is at 8.20. All right. If you compare the percentage of change for the 6 minutes is at 1.10. So the same applies for the whole base station, and you can see that the percentage of changes for all the base station was below 10% for each location. So taking into account of the 1 minute and 6 minutes. So if you can see specifically the percentage of change for 6 minutes compared to the 30 minutes time interval duration, it's only from 0 to 1.2%, meaning that the highest obtained was only at 1.2%, whereas in some in mobile base station number 2, specifically there were no any changes at all, meaning that the results was the same. You can see here, result obtained for 6 minutes was at 0.49 microwatts per cm square, and then the one obtained for the 30 minutes was also 1.49. So this shows that there's no percentage change itself, right? So the next is we need to compare with the reference level for the public. All right, as stated in the ICNIP and the MCMC standard, the reference level is at 1000 microwatts per cm square. So for this graph, the power density versus the location also it's shown that the highest is only at 1.84 microwatts per cm square, and for all the measurement points, regardless of the time averaging duration and regardless of the location, all is below than the permissible exposure limit, or it's below than the reference level of 1000 microwatts per cm square. You can see we get only 1.7, but for here it's the reference level is at 1000 microwatts. So generally it's less than 1000 times, right? The radiation level, right? So the next is we conducted in terms of specific or in terms of selective radiation meter, meaning that for each and every mobile base station, we have assigned the particular frequency, and also we can distribute what type of frequencies are there. Example, for all the this is the summary of all the 5 base station. So you can see that generally for all the base station, only 65% of the mobile signal in each base station is from the signal service provider itself. Example, if let's say at that particular base station, service provider M is transmitting the frequency, meaning that's only 65% is from that particular service providers. The others is from other service providers. Example, you can have from mobile phones, from our phones, or you have from our Wi-Fi devices, it's at 21%, and also from radio signals and also TV signals, right? So this shows that if let's say we are assessing any particular mobile telephone base station, the signal is not directly or it's not only from the telecommunication structures. There are also other environmental signal, also as I mentioned just now, from other mobile phones, radio, and also TV signals. Right. So now next we'll move on to the discussion. So based on this safety assessment, specifically on the 5 mobile base stations, so the percentage of change was below 10% for each locations. And then specifically for the 6 minutes, the percentage of change was at from 0 up to 1.2%, right? And then the range of the highest radiation frequency radiation level was found to vary between 1.30 microwatts per cm square up to 1.84 microwatts per cm square. So this highest level, it corresponds to only 0.18% of the ICNIP and the MCMC exposure level, right? So meaning that's very, very low. It's not even 1% of the exposure level. And then next is the radio frequency radiation are not only from the mobile telephone base station, they're also from different RF sources, example from mobile phones, radio, and also TV signals. So finally, the conclusion. So from this study, what we could come out was the percentage of change, POC, from the time averaging between 6 minutes and 30 minutes was very low, meaning that it's from 0 up to 1.2%, meaning that in some cases, the measurement, in order to get overall measurement, you can just measure at the time interval of 6 minutes instead of 30 minutes, which is a longer duration. However, more studies need to be conducted, meaning that there needs to be more data from more mobile telephone base stations and also from various sources of radio frequency radiation. Next is the radio frequency level measured in all the sites were below the reference level, all right, and it complies with the MCMC mandatory standard and also the ICNIP for members of public. And based on the findings, it's believed that the presence of the radio frequency radiation emitted by the antennas would not lead to any significant radiation exposure received by the public in the area. And one more thing to note, which is very important, is the radio frequency safety assessment should or must be done during the commissioning of new equipment or antennas, or when you perform or increase or add in additional antennas to the existing structure itself. All right. So finally, I'd just like to share certain research and study on radio frequency radiation health conducted by the ICNIP and also the World Health Organization. First is a common concern about base station. It relates to the possible long-term health effects that whole body exposure to the RF signals may have. All right. So to date, the only health effect from RF fields identified in scientific reviews has been related to the increase in body temperature, which it's a thermal effect from exposure at a very high field intensity. Okay. Keyword is high field intensity, found only in certain industrial facilities such as RF filters. So the one RF filters is generally used in industrial environment. Besides that, the levels of RF exposure from the base stations and also wireless networks such as our smartphone, tablets, or Wi-Fi devices are so low that the temperature increases are very insignificant and do not affect the human health. These are all stated by the ICNIP and also the World Health Organization. And so far, there's no any evidence in terms of usage of RF radio frequency radiation in terms of cancer, electrohypersensitivity, infertility, and also other health effects. Right. So before I end my presentation, I would like to express my gratitude to my technical staff, Mr. Zulkifli from Nuclear Malaysia, my two wonderful and excellent industrial training students, Ms. Noor Afifa and also Ms. Fatin Liana from UPM for conducting this safety assessment, although during the MCO time. All right, that's all from me. Thank you. And I'm very happy to answer any of your questions. Thanks a lot. And back to you, Dr. Shazwani.
Okay, thank you, Mr. Shamesh, about your presentation. Okay, so how about others? Do you have any questions regarding to this topic? I think this is a very interesting topic that that sometimes we keep on wondering whether the radio frequency could give any effect to us or anything. So is there any question from the audience? You can just unmute your microphone and ask directly to the presenter. So I think maybe there's no question, but I just wondering about the location that you did this research. Can you share with us where is the location that you did this?
Oh, okay, all right. So generally, it's this five mobile telephone base station is in the area of Bangi and Kajang.
In area Bangi Gajah, okay.
Yeah,
So is there
yes,
any
because
specific reason besides the antenna that you did the research on the area?
okay, first is because due to the MCO, I can just limit my students and also my technical staff around only in around this area. So maybe in future, if everything's okay, maybe if we have the enough resources, we can conduct in the whole over Malaysia on this research.
I see. Okay. All right. And I can see that this radio frequency does not give any effect to the human, right?
Yes.
Entirely, yeah. So
Yes, it's just at extreme cases, it just causes a thermal effect, which is a heating effect. That's it.
all right, okay. But is there any significant effect if that's, let's say in that area we have a lot of antenna and so on? Is there an increasing in terms of the comparison between the reference level and so on?
Generally, the more antennas they have, the more better, because when the exposure, when the EMF is high, meaning that our connection signal will be better. So when our connection signal, example, if to put the things into perspective, if we have more antenna, our phone bus will be maximum, right? So instead of you have a lower antenna and you're further away from the base station, the signal bus from our phone, it drops. So if you do a comparison study, the radiation from our it emits less RF radiation when the bar is full compared to when the bar is half, meaning that in other way, the higher the bar signal, the better, the less radiation we receive.
All right, I see. Thank you for your answer. And
right, thanks a lot, Dr. Sajwani.
okay, I think there is no question from the others. But if you have, again, you can just write in the chat box. Then I can read it before we end our session this morning.
Okay, all right. Thanks a lot, Doctor. I'll stop my sharing right now.
All right, thank you, Mr. Shamesh, for the presentation. All right, I would like to invite our next presenter from University of Malaysia. So he is Muhammad Adli Nur Azman. Are you there, Muhammad Adli? Okay.
Yes.
Right, so Muhammad Adli will present it on the nuclear fuel materials and its sustainability for low carbon energy system, a review. So without further ado, I give this screen to you, Muhammad Adli.
Okay, thank you, Dr. Shazuli. First of all, I want to confirm if you guys can see my presentation.
Yes, definitely.
Okay, cool. Okay, my name is Muhammad Adli. Assalamualaikum and greetings to Chairwoman Dr. Shazwani and fellow participants. My name is Muhammad Adli bin Osman. I'm representing my fellow authors to present a review paper titled Nuclear Fuel Material and its Sustainability for Low Carbon Energy System. So the content is the standard one. So we have the introduction to the issue that we're going to talk about, the global climate and everything. And then we proceed with the nuclear fuel material, also the spent fuel, volume and radiotoxicity. and we're gonna discuss that all the factors that we have talked and going to conclude it. On to the next. In 2019 alone, almost 85% of the energy consumption globally produced by the fossil fuel, followed by 4.3% of the nuclear, and the rest are from the various other renewable resources. The trend of carbon emission, as we can see from the presentation, was increasing since 1900, but in 2019, a slow declining trend was reported due to the incorporation of renewable energy. This increasing emission of carbon dioxide in average of causes the global temperature to increase above average up in mid-2021, as reported by the Global Climate Summary. So we can see that the increasing trend spells disaster to humankind. And as we experienced from 2020 and 2021, we suffered from the wildfire in California and the Black Summer of Australia. So in response to the climate issue, in 2015, 195 countries signed the Paris. In 2015, 195 countries signed the Paris Accord with aim to avoid dangerous climate change by limiting the global warming below 2 degrees and also pursuing the efforts to limit to 1.5 degrees. In the same year also, the United Nations General Assembly also introduced the 2030 Agenda for Sustainable Development, providing 17 Sustainable Development Goals for humanity and for humanity, planet, and prosperity. So as we can see from the graph, one of the goals is to develop an affordable and clean energy. The seventh goal, IAEA, the International Atomic Energy Agency, in their statements are quite confident that by harnessing the nuclear energy, the seventh goal can be achieved and therefore indirectly helps with the other 16. For example, we can, by being able to supply the industrial sector with a clean energy continuously, it indirectly provide the jobs opportunity and therefore helps with the poverty of the community, of the surrounding community. Before we talk further, we need to understand what happens during the nuclear reaction. So principally, via the fission process, a neutron is bombarded to a heavy nuclide, then split it into two daughter nuclei, and while releasing a huge amount of energy and 2 to 3 fission products at the same time, as shown in the figure. So in order to continuously producing the energy, a chain reaction is necessary. So this can be done by allowing other neutrons to collide with other heavy nuclei. From the graph, I use the uranium as an example, but we also have thorium and plutonium as the other commonly used heavy nuclei. These three horsemen can be further divided into two categories. The one is the fissile isotopes, such as uranium-235 and uranium-233, that requires thermal neutron to undergo fission process, and the other one would be fertile isotopes that require fast neutrons to convert the fissile isotopes to for the fission products. So according to the IAEA report in 2020, we have 430 reactors in operational with 52 reactors under construction. Most of the reactors currently operational is located in United States of America, but under construction, we have 18 of them from China. So we can see that China is slowly following the footstep of America, although we know that China is one of the biggest contributor to the greenhouse gases emission. We can see they are slowly changing they are rapidly changing to the renewable energy sources. So we also have almost 100 reactors that will be installed in the near future. So the advancements of nuclear material is essential to with the issue that limits the nuclear energy as the sustainable energy. Everyone knows about the infamous 2011 Fukushima accident, and this accident led to the creation of ATF by the Americans. This accident tolerance fuel, a set of a new technology that responding well when loss of coolant accident, just like what happened during the Fukushima, and reactivity initiated accident to prevent reactor from meltdown. This ATF also lower the cost of electricity over the license lifetime of an existing commercial reactor, according to the Nuclear Energy Innovation and Modernization Act, Section 107, also by the Americans. So some of the new technologies in ATF are coated cladding, doped pellets, increased enrichment, higher burn-up, and longer-term technologies. So other than ATF, we also have some other potential candidates for the advanced nuclear technologies, such as the fully ceramic microcapsulate fuel with tri-structural isotropic tracer particle. We also have uranium carbide, uranium nitride, and uranium dicarbide, which are also considered beside the light water reactor type. Another technology called high assay low enriched uranium, in short of HALEU, are also under big research project. By definition, that the fuel is between 5 to 20% of enrichment, and it is necessary for most advanced reactors to enable the smaller design to provide more power per unit of volume. So HALEU will also enable the developers to optimize their system for longer lasting costs, higher efficiency, and improve fuel efficiency. Next, we need to address the biggest public concern when we talk about the nuclear energy, which is the waste volume. The waste volume worldwide consists of major and minor actinides and short-lived fission product. Around 0.4% are classified as high-level waste, with half-life more than 200,000 years, which is around 150 tons of high-level waste and fission products being stored permanently in the fuel spent storage facility worldwide in 2006. And it is undeniable that the volume of the high-level waste will increasing and eventually becoming unsustainable for the nuclear energy to be harnessed, although we know that nuclear energy produces little to none greenhouse gases emission during the energy generation. So every problem has a solution. So a measure can be taken to fully or at least partially utilize the waste volume. Such measure is reprocessing of the useful actinides by the partitioning and transmutation process. Various studies have been conducted regarding the capability of PNT, and it was proven that PNT able to decrease the waste volume to a quarter. And as shown in the slide, that these two recent studies both prove the ability of PNT in helping with the waste management. One of the next is we talk about the characteristic of the nuclear spent fuel, which is radiotoxicity. So radiotoxicity is the parameter used to determine the toxicity released by the spent fuel. Both figures indicate that the first 100 years for both thorium and uranium core are being dominated by the fission product. But after 100 years, we can see that the radiotoxicity of fission product decreases and the actinides take the reign. Also, as you guys can see, we have a different of actinide line for thorium when we compare with uranium. This, for example, we have we have few peaks at such that happen in 100 years, a peak at 100 years, 100,000 years that can be investigated by evaluating the contribution of uranium-233 and its daughter. Also, uranium-234 and its daughter also contribute to the similar peak. So in discussion, we're going to talk that harnessing the nuclear energy aligned with the aim of Paris Accord and the 2030 Agenda for Sustainable Development. Low greenhouse gases emission is a tempting promise, not gonna lie. However, replacing all fossil fuel power plants with nuclear is not feasible and illogical. Sudden increase in nuclear power plant without a better system of facility will spells disaster or will spells doom for the spent fuel nuclear facility, storage facility, if not matched with the increase of nuclear power plant. But not everything about fossil fuel is bad. So for example, in 1970s, the fossil fuel companies are able to manage to reduce the emission of of carbon dioxide by introducing the carbon capture and storage technology, this CCS. Other renewable sources such as the wind, the solar, and hydro, making up to 90% of the total global power capacity. So by combining these three different type of energy resources, these three horsemen, so can definitely help with combating the climate issue. So in conclusion, nuclear energy is undoubtedly one of the key to overcome the climate change with its low carbon energy system. So major issues such as waste volume can be solved by utilizing the PNT process, as mentioned. Nuclear technologies with advanced nuclear fuel materials such as the ATF, not only addressing the current fuel concern, but also helps in reducing the waste volume, radiotoxicity, as well as the inevitable climate change. With its sustainable and clean properties, nuclear energy is a major option and an effective solution to the fossil fuel-dependent world in tackling the climate issue. And that's all from me. I would like to thank for the opportunity and attention. Hope you guys are having a great day. Thank you.
All right, thank you, Muhammad Adli, for your presentation on the nuclear energy as well as nuclear fuel material and also its sustainability. So quite a review. I think it's not a technical review on your paper regarding to this discussion and so on. But from your point of view, I just want to know that you show about the radiotoxicity just now. So between uranium and thorium, which one do you think is good to be used for advanced reactor technology in future? From your point of view.
Thank you for the question. So for this presentation, I didn't include the detailed comparison for uranium and thorium because it is too much detail for the review paper. But from my research, because this is the comparison of radiotoxicity is my main field for final year projects. So according to my understanding, the current technology shows that the thorium promise a low radiotoxicity for the first couple hundred years, but then reaching to 1000 and above, I can see the increase of radiotoxicity way above than uranium. So this can be reduced by reprocessing the actinides such as plutonium and everything, but of course by reprocessing the actinides such as plutonium, not only the good thing is they can help with producing the energy and reduce the waste volume, but the issue comes with proliferation issue because plutonium is a very dangerous actinide and a material used for nuclear weapon. So there's a strict rules for reprocessing the actinides of plutonium, and hopefully we can see in the future that maybe these rules can be modified for better use, and perhaps new technology, new nuclear reactor technology can also help with the proliferation issue when we're reprocessing the actinides.
All right, thank you for the answer. Yeah, it's good to see that about, because it's not that we can see that not everything is good for a longer period of time, but with the research and advancement we can definitely cope, we can overcome the issues and so on. All right, thank you Muhammad Adli for your presentation. All right, but before that, is the audience has any question regarding to Muhammad Adli's presentation on the nuclear fuel materials? I think it's not that technical review paper. You can just unmute to us. So I believe that there is no question from the floor. And once again, thank you, Mama Adli, for your presentation. And with that, we end our session 2 for this morning with the theme of environment and safety session. So and we have come to the half day for today. So I would like to thank you for all the presenters and also the participants for your time staying here. So we're going to take a break for a lunch. So in the meantime, please visit our website at iNUSTEC.my for poster and concurrent event information. You can look you can go to our website and see the poster by the participants, and you can also ask the question through their email and phone number given. So I think that's all for our morning session today. So we're going to see you again after this at 2 p.m. 2:10 p.m. So with that, I think thank you so much everyone and see you again. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, everyone.
still not here. If I'm not mistaken, he is an international participant. So it's alright. So he's the third speaker. So maybe we can wait. We can just continue the session without waiting for him. And also the last paper presentation will be my own paper. All right. So Dr. Lee Kui Wah, are you ready, Dr. Leo?
Yes, I'm ready.
Okay.
I share my slide.
Yeah, sure.
Can you see?
Yes, we can see it.
Oh no, I need to turn on my camera. First, how to? Okay. So could I start now or have to wait for another 3 minutes?
Do you want to wait for 3 minutes or you can just continue? Just start.
I'm not sure. Should I start?
Okay. If you can, let's start now.
Okay.
Right. The floor is yours.
Very good afternoon to everybody. So I think after the lunch hour, some of you might be a bit sleepy. Okay. So I will share with you some information about the latest design of the sun driver. It's quite a compact hadron driver. The purpose for the cancer therapy. Those are the name you can see here. Hold on, I try to. Okay, can you see? Okay, those the friend or the people involved in this project for the KK from the Japan, and Tanuja Digit, she from we call it Samir from Mumbai. So the outline for my talk, I will talk about the driver and the latest requirement in the parameters. Then before that we need to get the parameter of the lattice. So this I will show you some example, the method of the optimization to get the lattice parameter. Then some introduction of the current strider parameters. This is the basic for the lattice design. Then show the result and discussion, and last the conclusions. So I show this hadron driver. You can see in the table. So this is the parameter of the driver. That's in our design. So it's we're aiming for the 200 mega electron volts per nucleus. It's meaning A over Q is a 2. So the circumference is 22.8 meter. So the ion source we are expected for the gas and the metal ions. So which will be produced by the laser ablation ion source or the eclipse or the electron cyclotron resonant ion source. So this ion source will be located in you can see in the figure here is the ion source here. Then the injector that is the free without the free injector, or we call it the 200 kilo. We are using the 200 kilowatt electrostatics, just like we call it the column, extraction column, with some box inside the put each here with the ion source, all will be embedded inside the box. So the the design of the magnet is the 1.5 Tesla. So it's a fast cycling synchrotron, 10 Hertz. So we using the photo shell with the H focus for the bending magnet. So in this design is the mirror symmetric. Is from here you can see the kickers and the last dispersion flash region, which is the mirror symmetric. So those in this design or in this parameter that we have been determined, not just determined, we had to do the some optimization
but according to this parameter, the Bmax is 1.5. So the 200 mega electron volt per nucleum. So then we have this parameter. So then we had to get the parameter for those magnets which have been aligned in this ring. So this the things or the tasks we had to do. So I will show you. So the latest requirements of first I will I will share some information with the audience. So basically the lattice in the rings, so it's the array of the alignment or arrangement of the magnets around the pin line, which may consist of the bending magnets, polar magnets. Polar magnet might be the focusing or the defocusing magnets. So how can we arrive the magnets to get what's the parameter that we require in the ring? So typically the parameter that we need is the coefficient for the restoring force. We call it the K. K is we are depending the S. S is the position inside the ring. So in the K is the is a parameter dependent on the position on the ring. Also is dependent on the magnets. So in this case, so we had to get we had to optimize the K value inside the ring to get the ideal lattice or the desired lattice in our case. So can see the flowchart, how can we design the ring? So first I told you that we know the energy. So we had to determine the energy first. So we had to know the purpose. So maybe if we know the purpose, we need the position that is the fast cycling or the low cycling or how much the beam current requires. So it depends on the purpose or application. So then of course we had to determine the average radius circumference, which determine the bending magnets magnitudes, how many Tesla, so and the energy and the ion species. So that we can know the radius and the circumference. So then this another topic that is so we had to think about the injection, extraction, and acceleration. So we need to allocate the sun space for the injection device, extraction device, and the acceleration device. So typically, those are the space in lattice we call the bridge space. It's just the beam line without the magnets. So we can place our injection or extraction acceleration device inside such location. so you can see this process. So we have to determine the focusing magnet array. So then so this is the typically we call it those terms is the linear term. So for the maybe for much advanced or the detail, so we need to involve or we need to include the steering magnets or some commutativity correlation. So in this case, some space should be allocated for the such magnets. So that's why when we design a ring, we need to allocate some space for the such magnets or the devices. So you can see the some typical we call it the design. No, the design is the maybe is the some array of the magnets for the quadrupole. In the case one, we call it the photo. So photo, we can see we had this when the square drawing, you can see the QF is a quadrupole, focusing quadrupole. So the QD is the defocusing quadrupole. So when we had the focusing, defocusing, we call it the photo. So the doublet is quite, you can see when the focusing and defocusing quadrupole is arranged in such way, we call it the doublet. So the triplets, we can see we have the focusing, defocusing, and focusing. So this type of the array or the arrangement is quite famous or quite familiar to use in the accelerator design. So okay, for our design for this ring, so they have some very critical parameter. So the first we had to have some dispersion free region. Okay, about 2 meter. So, and second, we need the large dispersion fretch region around 3 meter. So the number 3 is we need some phase advance on the kicker to the sector magnet for the fast extraction about the 90 degree. So they are the 3 parameter or the essential requirements that is required when we design the ring. So what we try to do is that we optimize the K value, which must fulfill the three criteria. So okay, so for this headroom driver, we are proposing the extraction with the energy stripping technique. That means you can see the figure here is the Bmax. This vertical is the magnetic flux density of the bearing magnets. So the time you can see about from the starting lower energy to the extraction energy about 15 millisecond. So and you can see during the yellow the thing box here is the extraction during the extraction for the beam. So how can we extract the beam in our design? So we are using some momentum deviation. So what's the momentum deviation? So when we design the ring, so we had the ideal energy. So that means the beam should have some velocity or a momentum with respect to the energy, the ideal energy. So when but in real case, we couldn't get the ideal beam in the ring because we consist of the median or few medium beams inside the no beams is the particles that we call a beam. The particles inside the beam. So some of the particles they don't have the ideal momentum. So they might have the maybe a large plus minus 5 or 2 or largest when the momentum. So we call it the momentum deviation. We are not extreme at the ideal momentum or the particle that when we design the ring. So you can see in this equation, this expression of the x is the position inside the horizontal axis. So the d is the dispersion functions. So when we design a ring, we have some dispersion function, which are basically based on the bending magnet caused by the bending magnet. So you can see the delta p over p is some momentum deviation. So when we can see when the beam, okay, the important thing is that you can see that the dispersion region function is dependent on the S. As I mentioned earlier, the S is dedicated to the location of the ring. So inside each position, the D might be different. So when we inside the such place, the location of the ring, so there is this very large momentum dust dispersion function or the value. So they had some momentum deviation. So they will move to some position, this horizontal position, because they have the momentum deviation. And the design of the ring, they have some magnitude of the dispersion. So you can see in here. So you can see this figure, the bottom part is the beam core here. So in this location, just imagine in this location, you have some magnitude of the D dispersions. So the beam have some momentum deviation arrive here. So they have according to this formulation, so they have the excursion. From here in the center is the excursion is 0. So they will move, it's a negative, they will move inside here. So basically, this energy stripping method is based on the momentum deviation or the particles or the particle inside the beam and the design dispersion function at some specific location of the ring. So basically the ring, the particles will move inward here and arrive to some region we have allocated some extraction device. In this case, we are proposing the some carbon wire with some electric field. So for the extraction. So basically, when the beam will come here, because the beam will pass through the ring is no so many times. It's no one time. So the beam was basically some particle with some momentum deviation will be moved here slowly. So this is a reason why we need the large dispersion phase region criteria inside this design of the ring. Okay, so another design is the Betatron phase advance. So okay, when you can see this some current straddle ellipse here, so you can see for this methodology, so we twist the beam as an ellipse, so the beam will be propagate or turn around from the location inside the ring here over there. You can see. So for example, in here, let's say we had a location of the particle here. So after with the phase advance of the 90 degree, the beam, when we arrive here, they will go to the tops of the ellipse. So maybe you can see. So this the this express. You can see the beam will be have to go to the top of the beam. So that means they will become extract outside. It's outside the beam. No outside the beam. You can see it's outer of the beam side, so it can be easy to extract. So this is the requirement for the third requirement for the Betatron phase advance for 90 degree. So okay, we have the three requirement. Then we had to go for the lattice parameter design. No, so okay, we had to have some configuration for the lattice parameter. So okay, this is our lattice parameter. So in this case, our configuration are the shell 1, shell 2. So the center is the grid space 4, then shell 2, shell 1. So you can see this is the those parameter here for the D1, D4, D is correspond to the grid space. So the Q is for the quadrupole magnets. So F for the focusing, D for the defocusing. So this is the parameter. So we have we know the parameter, the physical parameter. It means the length of the grid space, and also the quadrupole magnets, also the bending magnet. So we have those parameter that we know. So but we actually we have to get the K value, the restoring force of the quadrupole magnet. That's why we had to optimize it to get this magnets. So in this according to this parameter, so we try to evaluate the two cases. So the case A is with the D3, D4 as a 0.1, 1.8 meter. For the case B is a 0.5 and 1.0 meter. But other parameters are still remain. So this is the optimized parameters. Oh, okay. So this is just the basic. We are using the transfer metric, which can be representative to every manage or the components or the lattice. So you can see for the respect body magnets. So body magnet, we have every day each focus. So this the transfer matrix for those component. So basically you can get this transfer matrix for in the AV extractor book for the differences. So okay, this is the basic formula for the transfer matrix. So when we can see the shell one, so we had those component, which can be represented by the combination of the transfer matrix. For the shell one, shell two, we have horizontal is a vertical. So we have the actually for this kind of this parameter, we had to consider the both side is the horizontal and vertical. So this is a formulation. So in this case, you can see the phase advance here. So in this case, we had to put get the tune because we are in this case we are just evaluate the half rolling, because the ring is the mirror symmetry. When we know the half rolling, we can know at the other side of the ring. So it's a fractional part of tune. So we had this formulation here, you can see. So we had to reach the very important parameter. We have to determine our optimization of the k value. So this the dispersion functions for inside the ring. So we bisa correspond to the some I, it means there's some component on the manage. So this for those cells which have been treated as a superpedic, as I told you, is the mirror matrix. So we have the shell 1, 2, 4, 2, 1. So as I mentioned that we have the two criteria here. So one of the criteria, one is here we have to get the very large sorry. Okay, this number one is the criteria, the red took here, is that we need to have the sun large fetch dispersion region. Number two is the free dispersion region. So the second stage we have to optimize the tune by the scanning the tune V. This is the dispersion region. Yeah. So we need to get this. Of course, we need to get this one. We need to get a large fetch dispersion region and the zero. Here. So we had to by using the tune as our parameter. So when you fit the n may be slightly modified. So we fit the horizontal tune because the tune is the very good measurement for the lattice functions. So when we have the note the QF1 and QD1, Russia 1, then we go to the first step until we certify the requirement by using the KD. So after they certify the requirement, we can use the QD2 for the sun tuning. So this is the just formulation that we for the tunes, personal tune, the formulation that we have. So this is the tune optimization by this chi-square formulation. So we can see the procedure to tune the adjustment. So we have to scan the small number. When we just randomly give the parameter of the k value. Then we have the some k value. So we have the try to scan by approximate a small change. So but in this case we scan the QF1, so we change the QF1, but the QD1 is fixed. So we had a try. So we had to when we have the three number, we had to have some parabola fitting by using the three chi-square. Later I will show the some figure. So after that we have the those numbers, and we can optimize the QF1. So then after that we have to optimize the QD1. So QD1 is the same. We fix the QF1 for the disk optimization. Then we scan the QD1. So okay. So after that we have the optimized QF1, QD1. So we as I said, so we in this case we fit the we optimize, we get the QD1 optimize of the QD1. So then if the chi-square, so for this formulation, so we had to test our result differently to get the optimization of the value. Okay, you can see in this figure it's much clear, so you can see. So in the right hand side is the optimization process when we have the try to the some number for the k value. So we have some parabola fitting, so we can get the optimized k value. So then for the optimized k value, so we can test our tune, partial tune, so we can get a number. Then we can put inside our lattice formulation to check the results. So okay, so this the
excuse me, Dr. Leo.
Yes.
You have 5 minutes.
Okay. This the cross-related parameters. So you can see in this Kuros area parameter, it's very simple. So we had some Kuros area parameter we can hear is the beta, alpha, gamma here. So at E is the emitter. You can see when I showed in the few slides before that. So the beam can be treated in the ellipse. So the particle will be going around inside the ellipse. Okay, so this is the some formulation. Also this is for dispersion function. So this is the result. So as I mentioned that we had tried with the three cases A and B. So you can see the red writing is corresponding to the difference for the case A, case B. So the others still the remain. So you can see in this value, so we have only the length of the finite dispersion region is the one. For case A is the 1.6, case B is the 2.0 meter. So we can get the what we as I mentioned that we had the we need the zero dispersion region. So we can get it. You can see it's the around 0 is a 1.44 power of 95 minus 5 for the case A, and minus power of negative h for the case B. So they also get the first advanced requirement for the fast extraction. So you can see the lattice we draw is the blue line is the horizontal beta function, the red is the vertical beta function, the green is the dispersion functions. So you can see the green one in the initial point or the starting point, we can get a large fast dispersion region. In the center is the zero free or we call the zero dispersion region or the free dispersion region. It's the case B. Basically, it's the same for the dispersion region. Maybe the beta tone function or the horizontal and vertical should be a different bit. So discussion. So this is the what we obtained for our optimization results. So we had the K value, so we can get the beta function, so we can know the maximum beta. This means it corresponds to the beam size when we know the beta function for the ring. So when we know the beta function for the each location in the ring, basically we will know the beam size of the inside the ring for every locations. So okay, this the latest design of the ring is initial or we call the starting point or initial task. So for the as a non-linear is a linear term, maybe evaluations, but for the further merge for the task, we have to consider the non-linear terms, that the perturbation for the chromatic study on the cross orbit distortion. Also the dynamic aperture study, maybe the caused by the bending magnet design. So maybe which will be affect the beam size. Also, that means when we affect the beam size, we had to check our beam design, the beam pi design. So the conclusion, so okay, so we had to design the lattice to fulfill the criteria, which is the three criteria they have been which I have mentioned. So this method that we use here, so it can be design the lattice is according to what we need. So for the future work, so we have to consider the non-linear perturbations. So but for the evaluation works must consider some engineering aspects when we come to the real parts when we want to design the manage. So maybe there is some constraint about the manage design. So that's why the some physicists need to avoid communication with some engineer in the when we want to design the sun ring or the magnet component to fulfill the requirement of the accelerator. So that's all on my presentation. Thank you for your attention.
Okay. Thank you, Dr. Leo, for the very interesting presentation on the Hadron Driver latest design. So we won't be opening the question session, answer question, but if the participants have any question, you can email Dr. Leo afterwards. So thank you, Dr. Leo, for the presentation. So we would like to continue with the next presenter.
Okay, thank you. So I will stop the sharing first.
Okay.
Stop sharing.
Okay. So next, we would like to invite Ms. Adila Hanim Aminuddin Sabri to continue the presentation of evaluation of scattering effects for radiation shielding or filter materials by using Monte Carlo simulation. Over to you, Ms. Adila.
Okay. Assalamualaikum and good evening. Thank you to the chairperson. My name is Adila Hanim binti Aminuddin Sabri, and my presentation today entitled Evaluation of Scattering Effects for Radiation Shielding or Filter Materials by using Monte Carlo simulation. So here is an overview of my presentation, including methods, result, and also conclusion. Okay. Okay, for introduction, most radiology departments utilize ordinary concrete and also lead for radiation shielding to reduce the primary radiation by the photon absorption or transmission. Then although primary radiation can be reduced, the photons might also be scattered either by transmission or reflection from the shielding materials themselves. Then lead, which is plumber material in the order of millimeters thickness, had been widely used since 1970 to attenuate the photons, either to shield the emissions of photons from the radioactive source, or used in a large scale to shade the room. And then while attenuate the photons, lead material, already known for its toxicity, expense and limitation in abundance. And then many scientists had proposed other materials to replace the lead element as gamma or X-ray shielding, such as clay. For example, Olukotun proposed the use of fabricated clay polyethylene composites for gamma radiations. And while our previous study proposed the use of gadolinium doped with polymeric as shielding material for X-ray. So in this study, FITS will be used to study the photon interactions with lead, iron, copper, aluminium, ordinary concrete, and heavy concrete, particularly for its attenuated and reflected photons. For methods, many studies have been done to focus on the ability of shielding materials, especially lead in attenuating photons for radiation shielding. And then, although lead is good in photon attenuation, it had been reported to yield the high amount of scattered radiation from the material itself at low energy incident photon. And then, therefore, this study shift the focus from photon attenuation to scattered radiation by evaluating the non-lead shielding materials that would yield the least amount of scattered radiation using FITS code. So for verification of our Monte Carlo code, with theory and literature data, we calculated the percentage of transmitted photons after the elements such as gadolinium and plumbum for single photons energy of 180 keV photons. So, materials geometry was modeled as rectangular shape with a pencil beam of mono energy photons was incident to the center of the element, as shown in figure 1. Then the distance was set at 10 cm from the surface of material. All the main photons interaction such as photoelectric absorption, Compton scattering, including the Rayleigh scattering, and pair productions were considered in our calculation. And then the transmitted and reflected photons using 6 different materials were calculated for incident photon energies ranging from 100 keV to 1 MeV. After that, the simulated linear attenuation coefficients from Monte Carlo calculation were compared to the values from the ESCOM in order to get the values of discrepancies. And then for the calculated transmitted photon for mono energy photon, Figure 2 shows the calculation of transmitted photons as a function of gadolinium thickness for a pencil beam of 150 keV incident photons. It has to be noted that Compton scattered photons that penetrate the material were ignored in our calculation for comparison with the attenuation coefficients generated by ESCOM. And then the full square points were fitted with an exponential function to obtain the linear attenuation coefficient values of 8.694 centimeters to the minus 1. For the linear attenuation coefficient, overall, the calculated linear attenuation coefficient value has a good agreement, which is within 1% with the ESCOM value as in table 1. And then this indicates that the linear attenuation coefficient value calculated by the simulation was reliable and verified to be used for the study of photon interactions between radiation and also energy within the material. Then next, the same code will be used to calculate the amount of transmitted and reflected photons in a wide photon energy range. Okay, for transmitted dose versus incident photon energy, figure 3 shows the graph of the transmitted dose as a function of incident photons energy from 100 keV to 1 MeV. So based on the graph, it can be seen that as the incident photon energy increase, the transmitted dose also increase for all the shielding materials. So this means that the higher the energy of the incident photon, the lower the amount of photon that can be trapped or absorbed by the shielding materials. So at 600 keV, the aluminium is lower within 13% compared to ordinary concrete. Then heavy concrete is significantly effective to attenuate photons compared to ordinary concrete, particularly at low energy region. Then at 400 keV, the transmitted dose from the heavy concrete is lower about 77% compared to ordinary concrete, while at 1 MeV, the transmitted dose from heavy concrete is 42% lower than the ordinary concrete. So in the case of an element, iron and copper show almost similar ability in photon attenuation as their Z number are close each other. At 500 keV, the transmitted dose for the copper is 100% lower than the iron, while at 1 MeV, the transmitted dose for the copper is 36% lower than the iron. Okay, then lead has the least amount of transmitted dose among other materials as it has the highest atomic number. So as a photoelectric effects is more dominant in materials with higher atomic number, lead can trap more photons than other materials, hence reducing the number of transmitted photon. For reflected dose versus incident photon energy, reflected photons are scored as a result of Compton scattering. As a result of Compton scattering photons with a large angle within the materials. So as the reflected scattered photons can be a source of unnecessary additional radiation dose to the patients and also workers that may stay inside the irradiation room or close to the shielding material. Therefore, it is important for us to evaluate the reflected photons in terms of their dose and energy. So from the figure 4, figure 4 shows a graph of reflected dose as a function of incident photon energy for shielding material, aluminium, iron, copper, lead, ordinary concrete, and heavy concrete. So based on the graph in figure 4, it can be seen that the reflected dose from all studied materials increase when the incident photon energy increase, except for the lead. Okay, although lead has the least transmitted dose, but at 100 keV, lead show the highest amount of the reflected dose among the materials, which almost similar to aluminium and also ordinary concrete. So this is because the low energy photon is unable to penetrate far within the lead material, which means most of photon interactions will occur only at the surface of the lead. So therefore, the Compton scattered photons could easily add the lead material as reflected photons. Then it was expected that the reflected dose from lead material will be higher for lower incident photon energy. Low Z elements such as aluminium and ordinary concrete, which commonly used as a shielding material, show higher reflected dose among other materials in wide energy range. And then as the thickness of material does not affect the intensity of reflected dose. Hence, a thin layer of suitable material is enough to reduce the backscatter. Then, in conclusion to my presentation today, an approach of photon calculation either outside or inside of an X-ray room must be considered when designing a radiation shielding to ensure radiation safety area. So when photons impinge on shielding materials, most of the incident photon energy is absorbed within the material, but some photons at certain intensity and energy value could be scattered or backscattered after undergoing Compton scattering interaction inside the material. So for all shielding materials studied, lead has shown the best ability at attenuating photons at every incident photon energy compared to other materials. So furthermore, the reflected dose will increase or higher when the incident photon energy increase, except for lead and for low Z element material rather than high Z materials. Lead element has shown as a high reflected dose in comparison to other material at 100 keV. Then, ordinary concrete that is commonly used as a shielding material for an irradiation room shows the highest reflected dose in a wide photon energy range. From a radiation protection point of view, the reflected photon component is important to be evaluated. This is because the concrete walls closest to the radiation source could likely be the more significant contributors to the scattered radiation at the patient location. So as a recommendation, the shielding thickness was kept constant to 10 cm, hence more study with a different material thickness are suggested to be carried out. So that's all for my presentation. Thank you for your attention and also many thanks to the iNUSTEC committee.
Okay, thank you, Ms. Adila, for the presentation. We have a question inside the chat. So first is from Dr. Leo. He asks, have you checked, by using fits, what is the difference between heavy concrete and ordinary concrete?
Okay, between heavy concrete and also ordinary concrete. It differ from its compositions. Also, also for its thickness. So in this study, we use the same thickness, but the composition density also is differ between the heavy concrete and ordinary concrete.
So how big is the difference between the two? The difference in density, maybe?
The difference is within 1% only.
So another question from Dr. Leo, have you checked the statistical error of fits after the simulation?
Yes, actually, in a full write up, we write down the statistical error of fits after the simulation. But in this presentation, I not include the statistical error.
So do you remember what is the error?
Let me check first.
That is in between like 5% or 10%.
Okay. Wait there. It's not more than 10% lah.
Okay.
The statistical error is not more than 10%. It's within the acceptable value. It is within the acceptable value.
Okay. So next we have another question from Dr. Amira. So can you share your future study based on these results? I think you really you did list one future recommendation, but maybe you can elaborate from that.
If I actually we already plan to do the future study based on this result, and if we have the result, we will join the another iNUSTEC next year, inshallah.
Okay, inshallah. Okay, so Dr. Amira will need to look forward to that. Okay.
Inshallah, thank you.
So thank you, Ms. Adila, for the presentation.
Thank you. Thank
Okay,
you also.
so we'd like to continue. with the next presenter. Is Mr. Adam here? Mr. Muhammad Adam? For the next presentation, the numerical solution of deuteron potential depth using a Python. Okay, maybe your supervisor, Ibrahim, Dr. Ibrahim, is he here? Okay, so I don't see their names, either one of them. So maybe we can continue with the next one, which is my own paper. Okay. In the meantime, we wait for them. Okay, I hope you can see the slides. If you have any question, you can just ask in the chat. All right. So this is one of the paper that I submit for this conference. So this is a very short paper. It's actually more on the, let's see if I can test it, okay. It's actually more to provide a tutorial, yeah, actually, oh, sorry. To provide the tutorial, okay, for anyone that have the same problem. Okay, so a little context for this paper. So I was when I was doing my PhD, I was doing the MCMP, okay, to optimize shielding using the MCMP and also a meta heuristic optimization technique known as the N colony optimization. But the problem that I faced was there are many studies that have done this type of optimization, but they mostly focused on using this NCMP and another meta heuristic technique known as the genetic algorithm. So I had a hard time to actually combine this NCMP to the algorithm that I want to develop. So this is the after I found the way to do it. So this is just to provide a tutorial. Okay, so that is the backstory of this paper. So for a little introduction, so we know MCMP is a very well-known nuclear simulator. Mainly, we can use it to simulate neutron and gamma or photon simulation. But this MCMP, the backbone, okay, or the principle behind it is the Monte Carlo simulation. So it is a very accurate, okay, very accurate simulator, but it is computationally expensive. This means that, okay, for a very complex geometry, when you have so many bodies of material, okay, with different density and all, so it will be it will take a long time to complete one run of the NCMP. Okay, the reason is because the simulator will have to actually track each particle, okay, from its birth to its death. So one of the things that we recognize, okay, is the new trend of using the NCMP, okay, using the NCMP for shielding optimization. Okay, as you will see later, I will show you some studies that have used this NCMP, okay, for this shielding optimization. All right, so this is actually the literature review. Actually, this is not the GA is not my work, my PhD work. I work on the ACO, but they two are like, not we can say like brothers or something, but they are two like similar. Okay, but each one of them has their own advantages. So that that's why I choose the ACO, because it's similar to the GA. So all of these studies has actually successfully combined this NCMP and GA. So so I don't know, but not one of these studies actually share the way on how to do it. Okay, so it goes way back to 2008. The GA is actually like developed in 1950 something, okay? But it's only recently in 2008 that they used the GA and NCMP for shading optimization. So you can see here, the first one, they use this technique to optimize file composite, and then another one used to optimize the arrangements for a multi-layer shielding. Okay, so multi-layer is we have multiple layers of different material. Like for example, we have 1, 2, 3. So we want to know what is the best arrangement so that we can achieve the goal that we want to achieve, right? So another one, 15 materials, okay. And also another one, we have the bismuth borate glass. So this one, this composite material, the glass, I don't remember. Okay, what are the things that they optimize? So maybe they optimize the content of bismuth, okay, or the borate, okay, in the glass. Okay, they optimize it until they get the goal of the optimization. And then the more recent one is these two studies. They use the technique to optimize seat shields, sheet shielding design from polyethylene, lead, and boron. And then the other one, I think this is the same authors. Okay, so they use it to optimize the 16 layer, okay, of multi-layer shielding. So this really shows the flexibility of the technique, okay, the meta-heuristic optimization technique. Okay, so for this study, it's actually to provide the tutorial on how to couple the NCMP, okay, with the Python. So Python is is a programming language. Okay, so using this, you can write the GA. Okay, so I actually did actually successfully do the GA using the Python, and also you can use it for ACO. I actually done it. All right. So for this paper, I add another thing. Okay. Aside from the tutorial, we did a little bit experiment, okay, so to see the effect of the multiprocessing, which can be done using the Python. So this multiprocessing, so generally, if you have the regular version of the MCMP, you can just run only one input. Okay, one input. Let's say this is one input file, and then you can just one at a time. Okay, if you have multiprocessing, okay, you can run, like for example, if you have two, you can run this simultaneously. Okay, so without waiting for the first input file to complete. So we have two setups for the experiment. So this is the setup. We have the laptop, okay, and then we have another one which is a more powerful desktop. So we don't actually compare these two. Okay, we actually just we would like to see the effects of the multiprocessing for each one of these cases. Okay, we are not actually comparing between these two because we know this desktop is vastly powerful than the laptop. So we know it is it will complete the NCMP runs faster than the laptop. So the laptop has 2 physical cores and then above threads. For the desktop, okay, we have 6 cores and 12 threads. And this is the base clock and also the boost clock, okay. So this is a little bit on the Python codes. What are the important things that we need to have inside the coding? So this Python code is written using the Anaconda. So this one is like a software, a distribution. So this one is free. You can download it on the internet. So why we use the Anaconda? Because it is very convenient. Okay, because we can use this and write our codes, and then you can just run you can run it very quickly and then get the answer. I mean, get the output for the code. So let's say you have an error, you can just simply very quickly see the error inside the code. So it's very convenient. And then also the NCMP input files also need to be written by the same code. Okay? It is auto written inside the Python codes. The reason is we need to have each input file, we need to have independent or a different random number seed for each of the input files. And in the codes, we have to import the multiprocessing function to enable the multiprocessing. And then for this function, okay, this one, the function is to enable the algorithm to access, okay, or to run the NCMP input, okay, because we know that NCMP, we need to run it using the command prompt, right? So using this, we can use it to call the command prompt to run the NCMP input files. So another one, another important function is the pool.starMap here. So this one is actually this is just, okay, we need to import the multiprocessing and then we call the pool.starMap. So this one is actually the code the line of code that enables the multiprocessing. Okay, enables the parallel runs of MCMP input. So this is the model. We have the source, which is the 1 MeV neutron. We have the simple sheet over here, polyethylene, and then the detector, boron trifluoride gas inside it. So we use the F4 tally for this volume. Then we can get the not the dose, we can get the fluence inside this detector. Okay, how many of the neutrons that is detected by this detector. So the number of history is 2 million. So this one is we decided on this after we have run a certain number of NPS. So we would like to have a number that will make sure that the statistical error is within acceptable range. So each one of each experiment, okay, will need to have 20 runs. Okay, so the experiment is to have the laptop to run 20 MCMP runs. Okay, and then we will see what is the completion time, and then we will compare what is the difference when we run the NCMP in series and then another one in parallel. So we know that in parallel, we expect that it will be faster, but how much faster? Okay, so that is what we want to find out. So here is the result. Actually, there are only two main graphs that I want to show here. So the first one is the effects of number of logical cores. Okay, if you remember, the laptop has only 4. Okay, actually, this is equals to the number of threads. Okay, the number of threads of the computer. So for the laptop, the maximum number is actually just 4. If you can see this graph in the green is the laptop, and then the red one is the desktop, and the blue one is also the desktop. The difference between these two here is the first one in the red, we kept the clock speed of the desktop up to 2.7 gigahertz only. So the reason is we want to estimate, okay, what if the laptop has more than 4 logical cores. So we expect that it will go like something like this, maybe, okay, if we had more logical cores. So at y-axis here, we have the completion time. So this is the time needed for 20 runs, okay, for MCMP. So what you can see here, actually, we see the curve, the trend. Actually, the laptop and desktop it's actually kind of similar. Okay, you can see the curve like that. It's not actually linear. It's not goes something like that. Okay, it's actually goes a non-linear way like this. All right. Okay, let me erase that. So the most significant improvement that we can see is going from one logical course is actually in series, and then we go to two logical cores. So this is where we start to do the multi-processing, or the parallel runs of SMP. So you can see just going from 1 to 2, from series to parallel, we can expect at least 37, the laptop 37.5% decrease in the run times. And also in the desktop is a little bit higher. Okay, so the difference might be in terms of other configuration of the desktop. Okay, maybe faster RAMs or the way that the commands of the CPU. All right. So remember this trend right here. And then we test on the effects of clock speed. Okay, what if we increase this, the clock speed from 2.4, 2.7, and then up to 3.9 right here. So we want to see. We know that it will be faster, but how much faster? Okay, so you can see at one logical core or in series, the gradient. Okay, this is the highest gradient actually, because when we add or when we enable the multiprocessing, the gradient actually starts to decrease. You can see the gradient like 1 to 1 right here. It will decrease to 66.95. So the improvement actually decreases, as we increase the logical cost. So we can see some diminishing returns, after some numbers of logical costs. All right. So for the conclusion, so we can expect that at least 37.5% decrease in run times if we use the multiprocessing. Okay, so going from series to parallel, we can actually expect this 37.5% in decrease of the run times. So if we have the choice, actually which one we want to prioritize? So actually we should prioritize the increase in logical cost. Okay, it has more significant improvement. Okay, as compared to the increase in clock speed. Okay, always prioritize the number of logical cores. If you can increase the number of threads in your system, it should be better. And also the last one, the detailed tutorial on coupling the SMP and Python was given. You can see in the paper, or maybe you can email me if you want the actual code. I can give you that, but you need to cite my paper lah, right? So that's all. Thank you. If you have any question. Okay. So let me see the chat box. And then also the participant, the previous paper, the Mr. Adam, is he still not here? Okay, Mr. Adam still not here. And Dr. Ibrahim. Okay. So if there are no questions, so the last session for today would be the keynote, keynote number 4. But actually, that one will actually start at 4. Okay. Right. So if there are no questions, I think we can end this session 3, and maybe we can have a break, okay, while we wait for the next for the final keynote to commence. So in the schedule, it's actually starts at 4 p.m. All right. So I will see you at 4. Okay. Thank you. Siapa pergi aku? Okay. So
Alright.
actually this game we have 10 questions. So the fastest and the most correct participant will win. Okay. So are you guys ready? Okay. So are you ready, Dr. Sazwani? Okay. So let's go.
Okay, ready.
Okay, congratulations to all the winners. Okay. All right, so maybe you can personally chat, okay, to the secretariat, okay, your name, your bank, and your bank account, right? Just put it. Don't send to everyone, okay? Just send to the one of the secretariat, okay? So we will, okay, maybe to Sajwani or maybe to Shahir. All right. So we will send the price straight to your bank account. Okay. So don't worry. The LHDN won't find you. All right. For the next keynote is Dr. Imran here. Okay. So let's wait for Dr. Imran. Okay, so we got some news regarding the last keynote for today. So Dr. Imran, he is not able to join us for this. So on behalf of the organizer committee, we would like to apologize because we know that some of you have been waiting for some time, okay, for that keynote. So we will end for today's conference for now. Okay, so we will see you tomorrow. The next keynote, okay, for tomorrow we will start at 9 a.m. Okay, we will have Professor Dr. Lee Dok Jung. So he's from Ulsan National Institute of Science and Technology, South Korea. So he will be talking about the nuclear core analysis and methodology development. Okay, so we hope to see you tomorrow. Okay, thank you everyone. Assalamualaikum warahmatullahi wabarakatuh, and have a nice day.
Thank you.